I would like to welcome you, people here physically at IT for Innovations and people online at another of our quantum computing workshops, this time aimed at photonic quantum computing. We will have two tutors. First of them is Zoltán Zimborás, who is professor at Helsinki University. And the second tutor is Zoltán Kolarowski, who is affiliated with the two institutions. One is the Wigner Research Center for Physics, and is also affiliated with the Department of Programming Languages and Compilers at Eötvös Loránd University at Budapest. So with this, I would like to welcome our first tutor here. And yeah, the audience, the podium is here.
Thanks a lot for the introduction. And yes, I'm now a professor of quantum algorithms in Helsinki University. But actually, I just moved there this year in February. And previously, I was also affiliated with those institutions in Budapest, right, where Zoli is. And we have been working a lot on photonic quantum computers and also building some good classical simulators of photonic quantum computers where you can test all those things that are going to go on. It's not a problem. There is a problem. So thanks a lot again. Sorry for not sharing the screen. So we have been working a lot on photonic quantum computation in general and also building quantum computer. And you know, I mean, photonic quantum computation comes in many facets, but one of the more near-term type of photonic quantum computation is about boson sampling and Gaussian boson sampling, and maybe trying to do some applications. And we are going to show one simple application in graph theory. It's still debated whether this has gives some advantage compared to classical methods. Maybe not, but it's still a good way to just look at it. So this will be what we are in general talk. And today, this will be the agenda. So we have prepared actually we have written very theoretical notes, like and then long notes that you can find on the Indico page. And actually, it's going to be updated during this workshop. But you can see where we are now if you want. And I'm going to give a little bit of a personal introduction to our approach to photonic quantum computations. Then there is going to be two sessions of introducing this concept of how one can deal with photonic kinematics, photonic quantum spaces, quantum Hilbert spaces, and how it's different from the qubit type of approach. It's going to be a little bit dry and mathematical, that part, but I try to still make it easy still. But after that, and after the lunch, we will have a hands-on session where we are going to actually break down those concepts that I introduced here, and with the Picasso simulation software, we will look at a couple of examples of exercises that we can do. And then after that, in the afternoon, there will be again some theoretical talks about certain states called Gaussian states, and which actually will play, of course, an important role in Gaussian boson sampling. And then there will be also, after the theory, hands-on tutorial. And we will follow a similar fashion in the second day. So in the introduction, my personal introduction cannot start with this basically simulation software, Picasso. This is photonic quantum simulation software that we have built with this great team. And actually, it's a team mostly composed of Hungarians, although there is also a Polish part of this. And actually, one of the people here, Tomek Rybocki, he took part on it. But the main person was Zoltan, the other tutor of this one. And actually, it could be seen that we have only working now because actually there appeared a paper very recently this year in Quantum where we describe this software system in a very detailed way together with the theory. But this is a culmination of a 5-year long work period actually. I just checked up when this idea became. Okay, we didn't have one line of code at that time, but we got actually some support from different organizations, mostly from Ericsson and QWorld, and of course our at that time home institution, Ötvös University and Wigner, and also we had a little support also from CERN. And we had an idea what to do at that time. Actually, it was even called something different when when we did that kickoff workshop. And very soon, and this was motivated. This was very soon after there were these quantum supremacy experiments by Google, which was on using superconducting qubits, and there were a lot of softwares appearing for qubits, but much less for photonics. Actually, I would say there was one good software, the Strawberry Fields, and I was thinking that maybe we should go into that direction, and these were the things like it offers a feasible quantum computing platform, and there are natural implementations of, for example, quantum machine learning ideas there, for example, the quantum neural networks. Also, it's easier to imagine distributed quantum computing with photonic quantum computers. And mostly my main motivation was that while there was a lot of competing at that time simulator softwares for qubits, and by now the de facto standard has become Qiskit and OpenQuasm 3, but for photonics it was much less. And now there are a little bit more, but still not so many. And we wanted to have all kinds of for all kinds of reasons we wanted to look at it. I mean, we were thinking of entering also experiments. I will tell you a little bit about this. And it could be good for cross-validation. Then we wanted to have also high performance computing, extendability, clean code, which actually Zoli made it really clean and it's very understandable. And actually we even have like a community building type of setup, how the user interface and the user experiments is, and it can be done. And soon after we started that kickoff meeting, this was boosted, and we didn't know about it, because the Hi-Fi group in China, the University of Science and Technology China, they made a big Gaussian boson sampling experiment with 60 photons in average. And after that came a couple of other experiments by Xanadu and everything. But 5 years later now, maybe you have heard the news, actually it was in August this month, the same group did now an enormous experiment with 3,000 photons Gaussian boson sampling. So now it's really there. Of course, this is a lossy boson sampling, so we also included those type of ideas there. So I'm going to go into what boson sampling and Gaussian boson sampling is later on in the detailed way, but what you should imagine, roughly just, is that you have a chip with all kinds of, where you can put, there are different photonic modes that you can put in, and you can put in a number of photons, let's say S1, S2, S3, S4, Sn in the beginning. Then here there is some type of gates, a circuit, a quantum photonic circuit. I will describe that circuit in detail in the theory session. And then we measure the particle numbers, what we measure here. And what happens here is that actually it's going to be equal to this circuit can be described by a unitary matrix. And from that unitary matrix, you can build up, depending on how you put in the photons here and how you measured, submatrix, and then you can also double or triple some columns and rows, and I will tell you that. And then you take the permanent of that matrix and the probability distribution that you measure this T1, T2, T3, T4, T5, Tn photons. So you plug in, let's say, you can say that it's 1, 1, 1, 1, 0, 0, 0, and then you measure 2, 0, 1, 3, 0, so on. The probability distribution will be actually related to the permanent of a matrix which is obtained from this unitary matrix that describes this interferometer here. And this should already ring a bell, because permanents are hard to calculate. In fact, they are very interesting objects. I mean, if you know this definition of the determinant, I mean, which we all know about how to get out using using, like in a chessboard manner, all the chessboard manner from each row, each column, one element from a matrix, and then multiply them together and sum over them. And if you put in a sign which depends on how you got out a plus minus sign these elements, this depends on the parity of that permutation, how you got it out, then you get the determinant. If you don't put in that sign, you just do this product of those elements and sum over all of them without the sign, you get the permanent. But interestingly enough, there is a striking difference between the two. I mean, this determinant appears in similar experiments with fermionic systems, which is a type of system that I'm not going to talk about, but in nature there exist either fermions or bosons, and photons are bosons, and you get this permanent, this probability distribution being connected to the permanent for bosons or for photons, and this striking difference is some people call it's the big dichotomy in complexity theory. So actually, to calculate the determinant, we all know how to do it. There is a method for n by m matrices, which is polynomial n to the n cubed. And for permanents, there are only exponential methods, and it has been shown to be sharply hard. So we cannot expect, in general, to be able to calculate permanents. And actually, Avi Wittgerson, a famous Abel Prize winner, called this dichotomy in complexity theory. This interesting fact that this is easy to calculate, this is hard, although they are very simple. And Scott Aronson was actually a postdoc in his group when he started to do quantum computing, and he knew, of course, about this, and he actually wrote a small piece called Avi Wittgerson's permanent impact on me, and it meant actually the fact that he was also trying to work on this, but on quantum computing, and he immediately realized that since in boson sampling these permanents appear, it might be a hard problem for classical computers. You can maybe do samples that classical computers cannot sample from that probability distribution, and in fact, he proved that. And then, just moving a little bit on, there was an other small development, which I will not exactly describe now, which was about doing so-called Gaussian boson sampling, where you don't put in a fixed photon number, but some other state, the Gaussian state, as we will describe in these lectures. And actually, that you could immediately use for certain type of graph theoretical problems, to solve certain type of graph theoretical problems. Namely, you could encode the adjacency matrix of a graph into the circuit in some way. And it turns out that when you measure these outputs, then the non-zero outputs then they will be connected to certain edges of the graph, and the more connected it is, so the more clickish it is, the bigger the probability that you don't get a zero there is. This means that you can have a dense graph sampling here, which is a very interesting thing. So this was our this is like what we wanted to look at and investigate, but also other photonic quantum computational schemes in Picasso. But we are not going to talk about the other schemes. We are going to focus more on these two schemes, boson sampling and Gaussian boson sampling, together with the theory. And we built this system. It has a very nice Python interface. You will see it in the hands-on session. I mean, it's very easy to pip install it and already play around, and it's super easy to do all those gates. We also have a connected a high-performance module with C++, and even we even have dedicated hardware at Wiener, actually FPGA hardware, which can make very, very fast simulations there. And not only that, we also are now connecting it to quantum computers. Basically, I can show it. Yeah, we want to connect it to quantum computers, and I will show at the end, actually at the Utrecht University, where Zoli is, they already bought such a chip from the Quix, a company called Quix, to which they will connect it. So apart from boson sampling and Gaussian boson sampling, the other features of our code is that you can do also universal optical quantum computer simulators with and without particle number conservation. And actually also you can simulate noise, thermal state, simple photon loss, which I will talk about, correlated photon loss. And we also try to build a community. That's why partially we are here, because the way we made Picasso was that it was made to be ergonomic and intuitive. You should have an ergonomic and intuitive programming user interface. We have also a drag and drop simulator online, and you can do shared repositories and collaboration, circuit design and community building can be done there. So in the hands-on session, you will see, but this is like a typical, very easy code that you have to build. And here you say that which modes you are affecting and what type of gate you are acting on each mode. You will see it later on. This is the drag and drop simulator where you have this nice picture of the phase space description of the state, which we will talk about next day. And as in the future, we want to have more quantum machine learning modules and plugins, tensor network backends. With the University of Pittsburgh, we are trying to work on that. GPU acceleration there. We have an internship program. Actually, right now, we have a very good Korean student working with us as an intern. And as I told you, that we are also hoping to connect this to photonic quantum hardware. And in fact, here is the hardware that we have at Utrecht University in Budapest. Okay, so I would say that that was my generic introduction to how we came into this business and into this topic. And I will start with the hard science now, but maybe there could be some questions here. Do you have any questions around this software tool or about photonic quantum computation in general before we turn on to the math part?
Okay. Zoltan, this device that you bought, is this a photonic device or is it?
Photonic device.
Okay, okay.
So we are going to actually connect it to this. It's partially, even we have some partial understanding how to do that.
Can you do Gaussian Boson sampling or only Boson sampling or both of those?
So in principle, that's actually a very good question. So in principle, it could do both of them, but what you need is not only the chip, and they are also buying other stuff. You need also the one photon sources for the boson sampling. That's a little bit harder, or squeezing for the Gaussian boson sampling. But in principle, the circuit could do both.
Okay, thank you.
Yes, and also you need detectors, and they both also detectors. I will comment on it later, but there was also a question here somewhere, right? Okay. No, okay, sorry. Then I can even comment that we are also a member of a consortium in Quantera consortium, where we are again providing Picasso as a hardware for some French basically companies which are more interested in photonic blind quantum computation. Okay, so then there are no questions. I move on to the harder part of this before noon session or morning session. Okay, so before I put that slide on, the main difference between qubits and photonic modes. I mean, if you go back here to this picture, this is a good picture, for example. You could have imagined that these are qubit gates, but there is a huge difference. The difference is that the input state here for qubits can be 0, 1, or an arbitrary sort of linear combination, which physicists call superposition of 0 or 1 with complex numbers. And also for these qubits, you can have that. And in photonic case, actually, this can be 0, meaning that you put in just a way, you don't put in a photon, 1, that you put in a photon, 2, that you put in 2 photons, 3, or an arbitrary linear combination of the two, which immediately tells you that as if you would have like already for one mode, infinite power, like you have an infinite Hilbert space or this infinite dimensional vector space, you can imagine, where you can do almost everything. I mean, you have big freedom there. But this is, of course, partially true only because while for qubits, basically you can have universal gate sets, and with those universal gate sets, arbitrary operations can be executed. For this case, of course, we have to pay a price because it's not true that we can do any unitary, because then really we would have infinite power. But then there are like a sort of physically implementable gates or unitaries, which I will talk about. And that's the hard part of photonic quantum computation with respect to quantum computation, that when you make this transition to a more meta language, like a more computational language, you still have a lot of physics information there. In quantum computing, you almost can forget about the physics. I mean, you have to, of course, know the philosophy of quantum mechanics, how to measure, what are superpositions. But if you digested those concepts, you don't need to know about the underlying physics. In some sense, this is the same for photonic quantum computation, except that the allowed gates are rather hard to describe, and they are related to what we can do physically. So I have to talk about that, and that's going to be basically the main part of these 2-hour lectures, and also the hands-on session after the 2-hour lecture. Okay, so let's formalize this. So if we formalize it, we can say that instead of a qubit, the elementary object here will be something called a Q mode, or simply mode. And And basically, we can have a number of particles, photons in there, in these Q modes, and it means that you can imagine that as a vector space where there are orthonormal vectors, and the first vector is the 0 photon vector. There is an orthogonal one with the 1 photon, 2 photon, 3 photon, and so on. And then it means that we can label with an integer or actually a positive, like non-negative integer number, the basis vectors. This will be the analog of the computational basis in normal qubit-based quantum computation. You remember in computational basis was for 1 qubit it was 0 and 1. For 2 qubits it was 0, 0, 0, 1, 1, 0, 1, 1. Here you will have 0, 1, 2, 3, 4, 5, and up to infinity. And if you will have 2 photons which will come, then you will have 0, 0, 0, 1, 1, 0, 1, 1, 2, 1, and so on. Okay, but let's talk about first one mode, one Q mode. So basically, this means that these different photon numbers will be orthogonal to each other. This just represents this notation. I hope you are familiar with it. This is like the so-called Dirac notation. It's okay, right? I mean, yeah. This means that they are orthogonal, and yeah, and then when now describing the allowed set of gates, there is a very important tool that the physicists came by, and these are the sort of creation and annihilation operator or ladder operators. In other creation and annihilation ladder operators. It's very easy. Actually, in this linear space, we give how it acts. So A dagger acts on n, bringing this basis vector n to the n plus 1 basis vector, but then you get also a square root of n plus 1 in front. And if you have the adjoint of this, the A, this is the creation operator, and this is the annihilation operator, you get, if you applied it to n, then it's going to be equal to n minus 1, so this is going to go to that vector, but then you multiply it with square root of n. And if it applies to the 0, then it annihilates it. So it gives you, this is like a vector labeled by 0, not the 0 vector, and then you get the 0 vector, so the not like nothing, the 0 vector here. Okay, these are very important operators because when I will describe the gates, I will use these operators. Okay, so let's now write these basis states, which are also called Fock states. These fixed particle number states, and the whole thing, this Hilbert space is called a Fock space, which is this Hilbert space. We can actually write this by, if we know that if it would be if you want to have 1, basically if you apply to 0 a dagger, then you get 0 plus 1 square root, so 1 times 0 plus 1 1. So actually a dagger 0 is the 1 state. And similarly, we can get the 2 state by applying a dagger 2 times, but then you have to renormalize because you get the square root of 2. And I summarize this here. Basically, what you have to do to get the n photon state, you have to put in the creation operator n times here, but you have to normalize it with this square root of n factorial. And then, of course, these are just the basis states, but any linear combination of these states are in principle allowed. Maybe we cannot get them physically. We will get them only those that, but in principle, you should be, if you put in enough energy and you have enough resources, you could get any linear combination here. So it's an infinite dimensional vector space. But of course, in what we have learned in quantum mechanics, that the coefficients here, absolute value square has to sum to 1. And if you measure in this computational basis, the particle number, I will come back to that. Then, of course, the probability that you get n particles is going to be Cn squared. So, of course, this has to be this normalization procedure. Okay. Another important tool here and concept is the so-called canonical commutation relations and the number operators. What are the canonical commutation relations? It just simply means that now we have defined what A and A dagger is. You can imagine them actually as infinitely big matrices. Basically, how you can see it is that A dagger looks like an infinite big matrix, such that everything is zero. You have zero in the diagonal, but just below the diagonal you have square root of 1, square root of 2, square root of 3, and so on below the diagonal. While A is the adjoint, so you have above the diagonal the square root of 1, square root of 2, square root of 3. You can imagine them like that. And then if you do the math, you will see that if you take A and A dagger and take the commutator, then you get identity. In fact, this should be a surprising thing, because if you would have worked with a finite dimensional space, you would not be able to get identity with any two operators if you take a commutator. Why? Because what you would be doing is that you have to take the trace of this and the trace of this. And if you are in finite dimension, then the trace just exists. The trace of identity would be the dimension. And here you will get, this is the commutator, of course. I hope you know this notation, but if not, it's like AB commutator is A times B minus B times A. Okay? And the trace of A times B minus B times A, or A dagger here minus A dagger A. If you would take the trace, in finite dimension, you can always do that. Then it turns out that the trace of AB is the same as trace of BA. So it has to be a zero trace operator. But here you have a trace D. So this could never happen in finite dimension, this commutation relation. This is like a very much an infinite dimensional artifact that you can have that. Okay, and this is called the canonical commutation relation. And then one more important thing is that is that we can introduce the number operator, which is like nothing else than A dagger A. And then if you act with this number operator on this n, then you get n times n. I mean, we can check it, of course, because if you act with the annihilation operator on n, you get square root of n times the vector belonging to n minus 1. And then you act with the A dagger, then you get again square root of n, but now instead of n minus 1, you get the vector belonging to n. So you get square root of n times square root of n. So n times the vector belonging to n. So actually the eigen, you can see these vectors as eigenvectors of these particle number operators with the particle number as eigenvalues. And then we will talk about, maybe I will mention it about later. We can talk about when we have many nodes about the total particle number operation, but we will, for that, let's go into systems of several modes. So in systems of several modes, everything is very similar. We just have to repeat everything in each mode. Meaning that now we will have the basis state can be that in each mode, you can think about like a photonic circuit where you have, let's say, 4 inputs. And in the first input, you put in a photon, or you put in N1 photon. In the second input, you can put in N2, N3, N4 photon. close. And this means that and the linear combination of this will be span this D mode Fock space. And here what you could do is that you can again introduce the creation and annihilation operators but now each mode will have a creation and annihilation operator. Yes, sorry. Yes.
Zoltan, let me be here representative of just dumb programmers, which I am. Can you explain whether there is a tensor product like between these modes, or there's lacking this like detailed information about mathematical structure, and this showed like you are using very shortened physics notation, which is sometimes confusing.
Here, we didn't have any tensor product. If you want the tensor product, I just say that as a state, it's, I could just describe without saying tensor product. Mm-hmm. You could also describe multi-qubit systems without tensor product. You can say that you have bit strings. Here you have, here you can say that you have non-negative mm-hmm. integer strings, mm-hmm. and they are the basis vectors. But indeed, if you want to put in tensor products, I just wanted to avoid that, then actually this Fock space, the D-mode Fock space, is nothing else than the tensor product, default tensor product of the one-mode Fock space. Mm-hmm. So there is nothing very special about it. It's just the tensor product of the default of that Fock space that I talked about. And this Fock space is nothing else. This one which is just a mathematician called it, if you need mathematical details, the small L2 Z, or in that case, if you, it's isomorphic, or you can do Z plus or M0 Fock space. So that's the L2 means that it's square summable, which means that this mm-hmm. vectors exist where this is a sum. But that I wanted to avoid a little bit. So this is like just a default tensor product. That's a good question. Any other questions? Just stop me and yes.
So one. The mathematical detail, of course, the global phase is ignored. So there is basically equivalence class here, or isn't it?
Of course. I haven't talked yet about that. That's true. So one thing here is that if you go here and in general to all also in the D mode case, I will write up the general formula. So this vector and the vector where you have e to the I phi, those two vectors will not be distinguishable by any expectation value or any measurement. So they are indeed, they belong to there is an equivalence class that they belong to the same state. Yeah. Okay. It's okay. Any further question? I actually didn't want to mention those things just to make the story more clean. So if that's a confusing thing about this phase, we can talk about that later if you want. You can just imagine them as vectors, these pure states at this stage. So what we do here is very similar. You can also imagine this as a tensor, an operator which is identity on all of these modes up to J and after J, and at J it's the A dagger operator, but we call that AJ dagger. And similarly, AJ operator is, you can imagine that as an A acting only on this one and as identity on the others. This is exactly expressed by these formulas. And again, you can have these creation and annihilation relations. Canonical anti-commutation relations. canonical commutation relations. The anti-commutation is with the fermions. And now what you have is that you have identity again if you are on the same mode, but if you are not on the same mode, they of course commute the creation and annihilation operators. And among themselves, they commute as well. So these are called the canonical anti-commutation relations for D modes. I guess there is no question again around this. And okay, maybe this is a little bit repetitive, but let me just to say it once again. You can again do exactly as Piotr said, that exactly due to this tensor product structure, you can actually write any of these basis states, these Fock basis states or particle number basis states, as the zero state, and you act with, if you have L1 number of particles in mode 1, then you act L1 times with the A1 dagger operator on the vacuum, on the 0001, and L2 times on the second mode on the vacuum, and so on. And then you have to renormalize again. And again, what we have is that the Fock space is now described by vectors of this form. Like it's, again, an infinite dimensional space. However, it has to be small L2 that is square summable. And in fact, the states that we are allowed, the pure states, has to be such that the absolute value squares of this coefficient, when you sum over them, have to be 1. Okay, and these, yeah. And these absolute value squares, these will be related to, of course, the probabilities of measuring particle number N1, N2, Nd. In a formal way, I mentioned this here. So what you can have is that you have a physical device called photon number resolving detectors, PNRDs. And then the probability of detecting in the first mode N1 photons, in the second N2, in the D mode Nd, in a pure state psi, where this is where psi is written like that. Okay, that's nothing else than you have to do basically the overlap between the vector corresponding the basis vector N1, N2, Nd with your state psi and take absolute value squared. But that's going to be nothing else than this coefficient absolute value squared. So this is the one, we will learn a little bit about measurements. This is one typical measurement that you have in quantum photonics. And we will hear about homodyne and heterodyne measurements. These will be other measurements. This is the particle number resolving measurements. There is also something called threshold measurements, where actually you just detect whether there is particle. It could be 1, 2, 3, 4, or there is no particle, 0. We will actually not go into that, but I can tell you that in Picasso we have a full module on that type of things. And right, what's the time? I'm just looking to, yeah, where one could cut off a little bit the story. So one thing that I want to define definitely are the so-called quadrature operators. They are nothing else than some linear combination of creation and annihilation operators, but they are very important because actually physicists use them, because this makes actually a connection between the so-called quantum harmonic oscillator, if you have heard about, and photonic system, a direct connection. And that's why they label it with XMP, so position and momentum, like in a usual oscillator. But here it has no physical meaning of position or momentum. We just call them like that. It has no meaning like that, no physical meaning. So the position operator Xi is AI plus AI dagger divided by square root of 2. And the PI is with the minus But to make it Hermitian, we multiply it to the minus I or divide it by I and the square root of 2. And these are called the quadrature operators. And these also satisfy a certain type of self-adjoint canonical commutation relations, which are here. These are just a consequence of these relations here. Right. And later on, when the other Zoltan will talk about Gaussian state and Gaussian Boson sampling, we have to introduce, and now as well, a little bit when we talk, we have to introduce these notations, which is very useful. So basically what we do is that when we have this psi, we look at that as a formal vector of operators. And first we have the annihilation operator, and then the creation operator. And then you can have the chi vector, which is a formal vector of operators, but here you have the X type of quadrature operators and the P type of quadrature operators. And you have this W matrix sort of that takes from chi to psi.
I have another question, please.
Yes, absolutely.
The index goes over systems or modes?
Very good. It goes over modes. It goes over or 2D. Actually, so the W will be actually 2D by 2D. So number of modes is D, yes. So it's a 2D by 2D system. And it's actually a very good point because many of our calculations, typically what we call linear optical calculations, are classically simulable because instead of looking at this huge infinite dimensional space, we can condense those type of calculations. These are very few, but we will talk about them into 2D by 2D matrix calculations sometimes. So that will be a very useful tool. Okay, so now we come to certain elementary photonic case and relevant Hamiltonians. The question is, how strict should we be with the schedule? Because one possibility could be that we make the coffee break now and talk about that after the coffee break. Would that be a...
You can change the time schedule.
Yeah, because that would be now I'm coming to these were like a little bit drier, and now it will be about the gates and what dates, and this is a longer product. So should we then... Yes.
Oh, so 15 minutes per...
Or 20 minutes, let's make it like that. So then we come back at... so now we will have a coffee break and we come back at 50, right? No, 20, sorry, 20. Okay, thanks a lot for coming back after the break. And so now we are gonna discuss the most important elementary quantum gates that are used in photonic quantum computations. And actually, we are even gonna go to something called boson sampling. We are also gonna touch that. And even at the final one, we're also gonna talk about how to include experimental photon losses in this type of picture. So before going to this Hamiltonians and gates, so once again, let us remind ourselves that we had a D-mode system, and we had thus the annihilation and the creation operators. Also, it means that you have D type of X type of quadrature operator and D number of P type of quadrature operators, and they satisfy those anti-commutation relation. And how in physics we do generate the unitaries that are then evolving the system is usually by defining the generator of that evolution, which is given by a self-adjoint operator called the Hamiltonian, which we are exponentiating I times Hamiltonian. That's going to be the unitary. So I'm going to talk a lot about these Hamiltonians then. So there are two very important and easily accessible and in the lab doable type of operations that on the Hamiltonian level are described by quadratic Hamiltonian and linear optical Hamiltonian. I mean, they are almost the same. It's just in the quadratic Hamiltonian, as you can see, what we have is basically a generic type of linear combination of a quadratic monomial of creation and annihilation operators, or a quadratic polynomial, sorry, of creation annihilation operators, or quadratic monomial of quadrature operators. That's the same set of operators. So you can have terms like AI square, or AI dagger square, or AI dagger A J, or AI AJ, or AI dagger AJ dagger, that type of terms. And the coefficient, we will call this Hij, and this is this formal vector, this psi of creation and annihilation operators. And of course, as I told you, we need this to be a self-adjoint or Hermitian operator. So the dagger of H should be equal to H itself. It means that this coefficient matrix, which is only a 2D by 2D matrix, so this is this H hat, it acts on this infinite dimensional Hilbert space, but the coefficient matrix is only a 2D by 2D matrix, can be described like that. And in order this to be a Hermitian operator, we have to have that A dagger has to be A, and B has to be equal to B transpose, and H has to look like this. Right, and this H, this 2D by 2D matrix, we call the Hamiltonian matrix of the quadratic operator. A little bit more general than this are the so-called linear optical Hamiltonians, which have this quadratic term and also a term which is simply a linear combination of creation and annihilation operators with coefficients such that we make them that they are made Hermitian. Okay, so yes. So one thing here is that what is important here is that those that are really, really easy to implement in the lab are these linear optical quantum Hamiltonians and the exponentiations of those. But an even easier set, a subset of these, are the so-called passive quadratic Hamiltonians, or passive gates. In general, a passive unitary is something that preserves the particle number. It means that if you take this particle number operator, you remember that Aj dagger Aj, that was the particle number operator of mode J, and the total particle number, so Nj, the total particle number is just a sum of these. So a passive gate will be a photonic quantum gate with a unitary operator, which is a unitary operator, which commutes with this total particle number. And let me introduce a couple of those gates. So the easiest one is just to take one particle number. That's it. It falls into this, like the Hamiltonian should be this one particle number. It falls into this category, of course, because it's simply Aj dagger Aj. And then the unitary generates is the exponentiation of I times phi. Phi is a free parameter, and Nj. Okay? And you can convince yourself very easily what happens if you apply such a gate on a generic, let's say on a generic state, a pure state. what will happen if you would apply to this state would be that you get phases to this C, but not the global phases Piotr was saying, but phases which depends actually on Nj. So you will get e to the I phi Nj there, that type of phase. So like you will have the same linear combination, but you will get an e to the I phi Nj, where Nj is this number here. So different type of phases for different vectors, or not necessarily the same for. Depends on that. And then I can describe this very easily, this operation. For the other type of gates, it's going to be a little bit harder to describe on the level of the state vectors. So instead, what we do is a trick that physicists often do, is that they instead evolve backwards so they say that I'm not interested now how I evolve the state itself, but what I could do is also look how the operators evolve, which is called like the Heisenberg time evolution. And if you look into how this gate, Rj dagger phi, Aj Rj phi, this is how you evolve an operator, how it acts on it. It basically gives you e to the I phi to Aj and e to the minus I phi to Aj dagger. This is how it will evolve. And everything, all the other creation and annihilation operators will be unchanged. So this is the so-called phase shift gate. I mean, of course, it gives you a phase shift for the vectors, depending on how many particle numbers you have in Nj, in the jth mode. Okay, then there is another very interesting gate. That's the very important gate and very easily physically constructible, and basically the circuits are made often of these two gates. The other one is the beam splitter gate. In some sense, it's very similar to a phase gate, but it's not like theta times or phi times Aj dagger Aj, but instead what you have is that you take two modes, Aj dagger Ak and Aj Ak dagger, and you make a skew Hermitian linear combination of the two and put a theta here. So you have two type of parameters here. It's an entangling gate, but it's still a linear optical gate, but it entangles two modes. In the tensor product formalism, it entangles. And here you can see how it acts. Basically, it acts as a small 2x2 unitary on the annihilation operators and as the complex conjugate of that unitary on the creation operator. So how does a 2x2, it's not a generic 2x2 unitary, but actually a special one where in the diagonal you have cos theta, and in the off diagonal you have this minus e to the minus I phi sine theta here and sine theta here. So basically like a two-parameter unitary on these two, and the U dagger on U bar on these two. So it mixes the two modes basically. That's what it does. And actually these two gates are universal among the so-called passive linear optical gates, which are quadratic gates that commute with the particle number operator. All of those H's which are of that form is called an interferometer. All of those Hamiltonians and the generated unitaries are called the interferometers. And you remember, once again, I go back. So like if you took a quadratic Hamiltonian, it had this coefficient matrix. Sorry for that. It had this coefficient matrix Hij, which is a 2D by 2D. And basically what you will have is that you will not have the B's here, because B's have these terms of AI, AJ, or AJ dagger, AK dagger. So dagger, dagger, or no dagger, no dagger. You will only have dagger and no dagger. So AJ dagger, AK, that type of Hamiltonian. So this is how the Hamiltonian matrix looks like. And basically, let's analyze this, how it acts on simple states. So first of all, I can tell you how it acts on an operator, like the Heisenberg time evolution, and then we look into how it acts on simple states. So basically, it turns out that if you do just from the commutation and anti-commutation relations, and we have the derivation in the notes that you can find in Indico, it turns out that if you would exponentiate this Hamiltonian, so e to the I h, you take that Hamiltonian here, and look at this quantity, how you evolve the AI, it actually will evolve it with a 2D by 2D unitary matrix. This is an infinite dimensional unitary matrix. This is a 2D by 2D because it only mixes the 2D creation operators and annihilation operators. And how is this U hat, which is an infinite operator, related to this U? Very easily, as you remember that H hat is this operator, but it has this coefficient matrix, which is just a 2D by 2D matrix, and it has this D by D block. And basically, this small U is nothing else than the D by D matrix. Sorry, it's a D by D matrix, and it's nothing else than the exponentiation of this D by D matrix. So this means already here that there is an infinite dimensional Hilbert space problem, but we can actually compress it, the time evolution in some sense, at least on the operator level, to a finite D-dimensional problem. So this is very well known. Of course, this is why linear optics or passive linear optics is very easy to simulate in a computer. This is the gist of it. And here what happens with the UI dagger. So then you could think that, okay, if I can simulate on the operator level, then it must be very simple. But it turns out that there is a catch. It's very simple only if you look at so-called homodyne and heterodyne measurements, which we will talk about later. But roughly, there are measurements about expectation values of X and P operators. On the other hand, when you make particle number measurements, something funny happens. Yeah, but for that, let's go a little bit slower. So first, let's see how this U hat acts on one photon state. So what is a one photon state? A one photon state is a pure state where the total photon number is 1, like it's an eigenstate of the total photon number with eigenvalue 1. But this means this is nothing else, basically, than just the linear combinations of vectors of the following form, that you have like 1 somewhere and zeros otherwhere, like in the D mode. So this is a D-dimensional space. And actually, you can denote it like EI, I going from 1 to D. It's a D-dimensional space. And let's see, this U respects this space, so it doesn't conserve particle number, so it will be an invariant subspace. And let's see how it acts on it. Okay, so what you can do here is that you write this EI is nothing else than UI dagger 0. You remember that if you act on the 0 is the vacuum, the 0 state, and if you act with the AI dagger, then you get the 1 here. Okay, and then what you can do is that you act with the U, but here you put in an identity, U dagger U. Okay, because U dagger U is identity. AI dagger 0 is just EI, so this one. And this is equal to 0. And we calculated already basically this. It's nothing else than UJI AJ dagger. So it's gonna be nothing else, a linear combination of these AJs. And actually this linear combination has the coefficients of a small, like this U matrix, which is nothing else again than e to the IA. So it's very easy to calculate the effect of this Hamiltonian on a one-dimensional, on one particle spaces. So we could maybe imagine that also in higher particle numbers, it's going to be easy. And we are very wrong then. Because what's going to happen there is that formally we can express it, of course. Okay? So basically, you can try to do U and N and act it, and then you can write N is N1, N2, N3, like a tuple of particle numbers, which you can create from the vacuum using the N1 times is you create so A1 dagger N1 times, then A2 dagger to the power of N2 and so on. With this normalization condition, you put in U. You do the same trick that you can put in U dagger U even somehow, and then the U0 doesn't change, and you have this. So it seems very compact. And I can even write this simple equation here. It seems simple, but it turns out that if I want to expand it in terms of the particle number basis, the expansion coefficients, which are nothing else than these values, so like how much, what is the overlap between M and N of UN? This is the expansion coefficients. These are actually going to be the permanence of, related to the permanence of submatrices from U. What are these exactly? Now I can tell you. So first of all, I introduce, the derivation you can find in the actually it's not such a hard derivation, and you can find it in the notes. What you have here is that you have this normalization. That's a very simple one. This is like how we do the normalization condition. And sorry, I take this away, this hand. Okay. What matrix permanent do we have to make? So what we should do here is the following, is that if we have N, like let's say that N1 is 2, N2 is 0, and N3 is 1, and M1 is 3, and M2 is 1, and M3 is 1, or something like that. It has to have the same particle number. Then what you should do is that whenever you have zeros in the M's, you delete the zeros column of the U. Whenever you have zeros in N, for example, in N2 we had 0, then you delete the second row of U. On the other hand, if you have in N1, M1 it should be 3, then what you do after the deletions is that you actually triple the column, the first column. And here you had N1 is 2, then you double the first row. So you do these successively, these steps, and you get the matrix, and you have to calculate the permanent of that matrix. And that's going to be the coefficient in front of M when you expand this UN. So while for the one particle case, it was super easy to understand this evolution, it's also very easy to understand this evolution in terms of creation and annihilation operators. When you want to expand it in terms of in this particle number basis and measure particles, that's going to be the next thing, then it's going to be super hard computationally. But the quantum computer just does it. However, we sample from it, so we cannot get out the permanent value. Yes, sorry. What the permanent is, you mean? That's what you are asking, right?
Can you please turn on the microphone? Talk to me. Just press.
Ah oui. Yeah, I wondered what is a permanent function.
Yeah, so like a permanent of a matrix, right? Yeah, yeah. So let me go back. That's a very important question. So what you do basically is that you take a D by D matrix, okay, A. You take an A matrix. Here is the expression, but I will explain what this expression is. And what you do here is that you take in all possible ways D numbers from this matrix in such a way that these D numbers, that if you look at one column and one row, or each column, there is only one number from your D numbers, only one of them appears in a column. Or in each column, there is only one number appearing, what you took out from the matrix. And in each row, there is only one that you took out from the matrix. Then you multiply these together, and then sum over all the ways you can take out these D type of numbers. In other ways, this is another way of saying it with the permutations. It means that let's make a permutation on the rows and permute the rows of A, and then take the diagonal numbers and multiply them together. This is what it says. And then you sum over all permutations. But that's the same thing what I said. You know, like the determinant, there is this formula for the determinant, which is very similar, but with actually a plus minus sign depending on that permutation sigma, whether it has a parity +1 or -1. Did this help, or does this help, this formula?
Just a bit confused on notations because you have a perm and pair, and they say two different things, right? Permutation, you said here, and the previous one was permanent.
So Aij means the matrix A, and Aij means the entry in Ij, in the Ij entry. Like you understand, you have a matrix, D by D matrix, and Aij is the entry belonging to row I, column J. Is that okay? Okay. And now let's be very formal now. I tried to be less formal, but then let's be very formal now. Then what you do is that you have this matrix, and then you consider, this is a D by D matrix, all the permutations of D element objects. So 1, 2, 3, 4, 5, D, these numbers, all the permutations of these numbers. Okay? And then what you do is that you build up a new matrix, which is obtained by acting on the permutation with the first index, which means that you permute the rows or the columns. It could have also been here or here, the sigma. Okay? And then you multiply the diagonals in this, and for each permutation you do that and add those numbers. But that's, I think, a confusing way of saying it, but now it's at least understandable because I give you all the thing. The less confusing way of saying it is that you think of it as a little bit like a Sudoku type of thing or whatever. So you have a D by D matrix, okay? And you take out D entries from these. But these D entries you take in such a way, so you have D square entries, but you consider only those D entries where in each row you have one of the D entries, and in each column you have one of the D entries. You can imagine, for example, a 2 by 2 matrix. In a 2 by 2 matrix, you have to take out two elements. One way of taking out two elements is you take the two diagonal, because then in the first row there is only one element, in the first column there is only one element, in the second row you have only one element, in the second column you have only one element. But you can also take on the off diagonal. There are these two ways. and then you multiply the diagonal and you multiply the off diagonal and add them together. That would be the permanent. The determinant would be very similar, but you would add a sign. Actually, you would add a sign corresponding to this permutation, and that would be. And for bigger matrices, you can use the same rule that take out all these ways. You can take out D elements such that they are these entries these D entries are placed in such a way that in one row you have exactly one entry, and in one column you have exactly one entry. Okay, that's the way. And the funny thing with this is that determinants we are always used to calculate, and this is very easy to calculate determinants. Well, n to the power of 3. Like on the border of being easy, let's say. But this is super hard. This is in the worst case. In the worst case, it's exponential, and I think even there is no like square root 10 or something. It's just exponentially hard to calculate. It's sharply hard. And it's also a really annoying thing because many things in mathematics are connected to this. So for example, in bipartite cases, the bipartite graphs, the number of perfect matchings is related to the graph's adjacency matrix permanent. It's a positive matrix. You have many methods for positive matrices, but even that number is not known. Actually, you know that this number of perfect matchings is in co-MP. We don't even know whether it's an MP. But this is sharp in general for generic matrices. And this is, and I told this joke in the beginning, and it's not a joke actually. Scott Aronson wrote this Avi Wittgerson's permanent impact on me, that when he learned about this interesting thing, and he was learning about quantum physics, he saw how these occupation number probabilities in fermions are going with the determinant, while for photons, for bosons, it goes with the permanent. And that's how came up with boson sampling, which I'm going to talk about now. But it's okay, I answered your question, right? Yeah. Yes. Yes, yes, yes.
So I also have the question about this RMN, because
that's an important
question. That's not really clear what you mean by that. Is it a matrix, or is it an operator acting on a matrix or function of a matrix?
Yes, so RNN, I described it very informally. It's not a matrix, it's an operator acting on the U D by D matrix. And it actually makes a matrix which is as big as many particles you have. That's why the particle number is the important number in this. So the total number of particles in N is just N1 plus N2 plus N3 plus ND. So that's from U, it's going to make a matrix like that. And M, this is non-zero only, this, if M has also the same total number of particles like N. So N1 plus N2 plus N3 plus ND is the same as M1 plus M2 plus M3 plus MD. So the same number of particles, okay? So it's going to make from U a matrix which is, let's call it big N times M matrix. And how does it do? It's a procedure how to do this matrix. Basically, what you do is the following: is that first you take M, okay, and then that will do something in the following way with your U. What it will do is that it will go through your rows. So if M is 0, M1 is 0, then it will delete the first row once and for all. It's deleted. If it's 1, it just leaves it invariant. If it's 2, it doubles the row. If it's 3, it triples the row. So you go through the first M1, then M2, it does the same thing with the second row. And M3 with the second, third row, and so on. And after you are done with that, you have an N by D matrix. And that time you go to N, and N does the same thing with the columns. So you either delete the column or make double the column or triple the column. That's what this RMN is doing. So it creates a complicated matrix from this U by deletion of rows and columns or multiple like copying them. Okay, so it's not like an easy thing. Tomek worked a lot on this actually, this thing. Okay, and what the important thing is now is that I described this generic U, which has this very complicated output probabilities. These will be basically the squares of these will be output probabilities. But this U can actually be decomposed into this elementary gate of a phase shifter, RJ, and beam splitter. In fact, this means that these two gates are universal among the passive linear optical gates. They can be expressed everything. In fact, actually, it's only up to depth D that you have to go. And this is called the famous Clemens decomposition, which, by the way, is not so old. I don't know Tomek Kurzoli when it's from, but it's 2000 something. There was previously another one which was used the same number of elements, but in a clumsy triangular way, the reconciling decomposition. But this is a much more modern, but very well cited paper. And what you do here is that actually what you have to do is that basically you do D times D minus 1 what are they called? These beam splitters, these 2 qubit gates, these are entangling gates. So the photons, these are you can see the modes. So here is one mode, the second mode, third mode, fourth mode, fifth mode, sixth mode. And then this follows this line. And basically what it does is that this entangles these 2 modes, this entangles these 2 modes, and so on. And at the end, we add a phase shift. And these together actually gives rise to any interferometer. Good. And now I come to boson sampling once again, because basically now we are ready to define what boson sampling is. This is not the Gaussian boson sampling, we will also talk about that, but the usual Aronson-Arkhipov boson sampling, which is that we start with a state, fixed photon number state, N1, N2, Nd. Let's be honest here, it's very hard to do. Vacuum is very easy, so if N1 is 0, that's very good. N1 is one photon state is hard. It's pretty hard to do, but doable. 2 photon state, only the best of the best can do a 2 photon state, but it's still people can do it. Pure 3 photon state, nobody can do. People can do a linear combination of those, but the pure 3 photon states, nobody can do. So I mean, of course, in theory, we can have N1, N2, Nd. And Tomek put in those 3 L2s actually, but in reality, what you will have is just ones and zeros typically, or you can have 2. On the other hand, so you put in that, but I will talk about the measurement. That's going to be an interesting point. Exactly. So although n can be arbitrary, the values of ni are typically chosen to be 1 or 0. And then these photons are passed through a generic passive linear optical interferometer characterized by this D times D unitary, which I mentioned. So this one, you can see also those chips in these experiments. And it preserves the particle number, and then you measure the output. Like what the output is, M1, M2, MD. And here it's important that although I denote the output as a vector, usually these photon number measurements are like destructive measurements. So you get that there were 2 photons, but they are lost. And here actually there is often a phenomenon called boson bunching, meaning that actually, although you started from 1, 1, 1, 0, 0 or something like that, it's actually the collisions that you get 2 is not so few. So 2, 3, you get those collisions here. This is what called collisions in this, that you have measuring more photons in one mode. But you cannot generate a state like that because you are measuring it and destroying it. Okay? And the probability is given by this formula that I told you. So basically what you have to have is the square of this permanent that I described. So that's boson sampling. And this, then you can say, wow, so we can calculate permanent, but this is not true. Oh, yes. Yes.
Sorry, physicist. When you speak about collisions of photons, I start to jump. Can you define this again?
Yeah. Collisions means it's a jargon, like a word of like how people are discussing it. It only means, it's not very simple. Collision means simply that in the measurement, you don't get ones and zeros, but let's say a 2. That means that you have a collision, It's just a way of saying it. Like you have 2 photons, you measure 2 photons there.
No physics.
No physics, it doesn't mean a collision. It's just a way of saying it. The reason why...
It's just there can be collisions between photons, but at very high energies. That's why.
Yeah.
Okay.
No, it's not about collision of particles
All
or
right.
something like that. No.
Thanks.
It just says usually what they use is collision free means that you have only ones and zeros. And that's what it's called, collision free. And then you ask, why is it important? It's important because often the theoretical analysis can be done very well. I mean, Zoltan here is doing it, for example, for the different type of setups, for the collision-free cases. So when you assume that you don't have a collision, maybe you can post-select and you can consider all those cases. Then you can say more about the models. That's all. It's just a way of saying.
So it's a mathematical collision.
It's a mathematical collision. Nothing.
Like in a manifold, you have 2 things which are like similar.
Yeah, I mean, you get a 2 here. It's that just that, not 3.
So
Not like ones and zeros.
kind of degeneracy in a sense.
Yes, in some sense, yes.
Okay, thanks.
Okay. Okay, but I wanted to get to also a very important point here. So this is hard to calculate, but it doesn't mean that the quantum computer gives you out this. Why? Because, of course, you have exponentially many possibilities to get out these samples. So you cannot estimate just in exponential time this probability. You cannot estimate it. However, in the time of generative AI, we are used to something called sampling algorithms. You can ask a different question. You don't want to estimate this number, but you say that for some reason, for some strange reason, I want to make an algorithm that gives me samples with this probability. So it gives me non-negative integer values with this probability. And what Arkhipov and Aronson showed was that actually, if you would have such a classical algorithm that produces such samples in polynomial time, in the number of, let's say, in the number of photons, then what you would have is that in some complexity classes in the polynomial hierarchy that people, complexity theorists are expecting not to collapse, to be the same, would collapse. And then if they would not collapse, you cannot build such a classical algorithm. It's a little bit like a generalization of the, sometimes you prove that this is MP complete, this problem. This means that if P and MP is different, you will not find a polynomial algorithm that runs that. In a generalized way of that, they prove that you cannot sample with these probabilities. Then, of course, it was called like a supremacy scheme, and people were thinking of, well, okay, I mean, it's interesting, and of course, there are these huge experiments with 3,000 modes done, what that I mentioned here. Where was this? Well, this was, yeah, here, for example, here for 60 modes, and now In August, we had 60 photons, and now we have 3,000 photons. But is it useful? But then people have tried to build applications, graph theoretical applications, applications in optimization, molecular docking, and even more recently, we are doing, and other people have also touched a little bit, they have done like generative learning, can you maybe learn something interesting that classically you cannot learn, some interesting probability distribution. So there are some ideas floating around. There is no proof of a real useful model that you can get out from this sampling. There are some like tries, which we will show, this graph finding dense subgraphs. That's a good try. There is no proof of that, how it's related to classical algorithms. Okay, so that's it. Okay, and yes.
I have a question. Will you talk about benchmarking of these probabilities in this talk?
Very nice. That's like the key question in this business. How can you even benchmark it?
I mean, for example, something like heavy output generation.
Exactly. Very good. Very good.
Okay.
So this is the great thing. So if you like at the same time, then boson sampling appeared, many similar schemes appeared. For example, there was the random circuit sampling, which also had output probabilities that you couldn't calculate classically, but you would not be able to measure it because you would have exponential, or the instantaneous quantum polynomial circuits, IQP circuits, where you had, and Tomek's ex-supervisor and me, we built the fermion sampling, which is a similar thing. And all these schemes are such that that it's very hard to benchmark them. What I can tell you that there exists no rigorous certification if you only look at the samples, but if you trust your detectors and do some gates, and well, I'm not going to tell you, but if you trust the detectors and you have a state and you do some other gates, which you also trust, then you can verify that you have the correct, let's say, state or things like that, both for boson sampling and for Gaussian boson sampling and also for fermion sampling. So there is that type of verification, but only from if you don't trust a detector, then only from the outputs, you don't have a rigorous certification, rigorous verification. Nevertheless, you can have some benchmarks, and exactly what you are saying. So you can have the heavy output benchmark is on its own very hard because you don't know which are the heavy outputs, but you can build up like a type of cross entropy benchmarks, which somehow you calculate some average quantity, which if it would be a boson sampling, it would be something, but it doesn't give you a rigorous, it's just say that it's compatible. And another thing that they are doing, and they did heavily in this hi-fi experiment, is that they measure average values of particle numbers, because actually the average value of one particle number, or N1, is easy to calculate. You cannot sample, but the average value you can say, or even N1 times N2 you can do. And then you calculate those average values, and that's like, you cannot sample, but you can at least see that it's compatible. So that's the best thing you can do.
But you say like it's easy, but it's easy classically, right? Yeah, because what I'm thinking is like we are sampling and we know it's hard to do classically, so we would need to have some kind of proof of correctness that actually doesn't require classical computation time, but also it cannot be like faked because of some classical outside simulation. Like, is it possible to do something like this?
So I claim that you cannot rule it out. However, I claim like you said, this could be like a little bit
like for example, let's say there is this circuit made from this beam splitters with some phases, and let's say I think on some particular setup of phases that I can predict the distribution because I choose this, but somebody who doesn't know my mind setup cannot do classical simulation easily. But then we run this on computer, I mean on the on this hardware, and we see, oh, it match up. So our like we have a real system, right? Like a real quantum system.
That you can do, or you can even hope for a zero knowledge proof type of
something like this, exactly. Yeah.
A lot of samples I can verify, but I cannot sample myself. So what I can tell you is that there is at this stage no such protocol. They tried it for IQP circuits. There is this beautiful paper by Bremner and others, but then David Gross and students, they shut it down. I mean, it was a heuristic thing. But what I can tell you, if you allow extra gates and you trust the gates and the detectors, you can at least test it at that state, and you cannot sample. But just from the samples, you cannot do it. You have to do these trusts. And that would be a very key point if you have that type of
circuit. Okay, but do you think it's like, do you believe it's doable? Like, or there is some maybe limitation that is not existing, like?
For the boson sampling, generic boson sampling, generic IQP sampling, random circuit sampling, of course not. But I would say no in that strict sense when you don't have this trust. But what people are trying are to look for instances, a little bit what you said. So instances with more peak distributions and where you can have something like that. And I mean, it would be a key. If somebody would show it, that would be a huge thing. So I can refer to you, I can give you later that there was this, actually it appeared this year in PRX Quantum. There was a paper by Bremner and collaborators where they said that for certain type of IQP circuits, where they put in some secret, actually. They knew the secret, and they would be exactly as you say, verify from that secret, but nobody could find out that secret. And then David Gross and collaborators came with a new paper, and they found the secret. Actually, they run it, and they found the secret, and they showed how to do it. And now people don't know whether you can do it. But it would be that's a key point. So right now, everything what the Hi-Fi group and everybody is doing, you're not doing strict certification verification. They are doing some benchmarks, I would say, some type of partial verification. That's a key point here. And right, so let me check a little bit time, just to see how to proceed. Yes. So basically, this is boson sampling, but it turned out that boson sampling, the experiments are not usually doing boson sampling because with usual boson sampling, it's very hard to produce those one particle states. I mean, you can do it, but then to do a large scale experiment to at the same time produce, because you have to have these going into the interferometer at the same time, let's say 3,000 one particle state, like you cannot do. What you can do instead is to do something called Gaussian boson sampling, which will be the topic actually after the lunch. But for that, I need to introduce gates that are not particle number conserving, which are usually hard to do in the circuit itself, but before applying an interferometer, these are not so hard to make. And yeah, these are like active gates. So these are, which is particle number conserving, they are called passive gates, and these are called active linear optical gates. And one gate is this squeezing gate. So the squeezing gate has a Hamiltonian of this form. So it has like AJ square and AJ dagger, and you add them together to get an I times the Hermitian, so a skew Hermitian operator. So this is a complex number here. And this mixes up, of course, the creation and annihilation operators. And actually, this mixing matrix is a very important type of matrix. I mean, in this form, you cannot see it really. But if you look into the quadrature operator, how it acts on quadrature operators, it's e to the minus r and e to the r. And we will later have other types of gates as well. And this will all generate something called matrices, 2D by 2D matrices that are in the symplectic, real symplectic group. But this will be real only in the X and P, X and P basis. So this is the squeezing gate. So why is it called squeezing? So tomorrow we will learn about the Wigner phase space representation, the Wigner functions. And if you act on the vacuum looks like a nice Gaussian function in that representation. And then this gate squeezes the vacuum. It looks like a Gaussian, but squeezed in one direction and elongated in the other direction. So that's why it's called like that. And the other gate that is important is the displacement gate. And that's actually just a linear gate, meaning it's a linear combination of AJ dagger and AJ. And what it does is that it basically adds an identity times a number to the AJ and also the identity with the alpha bar to the AJ dagger. And yeah, this is how it acts on the quadrature operators. Right, and together these two gates, and so the squeezing and the displacement gate and the beam splitters and the phase shifter, these four gates, which are, we will see they are in Picasso as elementary gates, they are universal among all linear optical gates, actually. So not necessarily just particle number preserving, but non-preserving those gates. And actually, you can also do similar decomposition as the Clemens decomposition using these. And then there is one more important topic that I want to touch on, and we will have an exercise on that. And that's about the losses. And sorry that I'm picking you, Tomek. Tomek is also great on the losses. In the Picasso, he was working on these losses. And on the losses. And there is huge amount of losses in linear optics. What the good thing with the losses is compared to much bigger losses and errors than in let's say superconducting qubit quantum computers like the IQM that you have here. But there is one good thing about though, is that actually we know quite precisely how they look like because these physical procedures are always the same. And this is how you can, and basically the main error component is photon loss. That's it, photon loss of a mode. And this is how it looks like. So actually how you can model it, but this is how it really works, is that you can model it that the photon goes to the environment somehow. And actually you can look at it that the environment has like one mode. Environment is only one mode. I mean, if you have D modes, you have to have, of course, D modes. I mean, the environment has infinitely many modes, but it goes into one of those modes. And basically, how it goes is that that there is a survivor, like if you take, let's say, a chip, and let's say during the full chip, there is maybe a survivor probability eta of the photon, and then there meaning actually that yeah, survival probability eta and 1 over eta that it gets lost, and it is modeled in a way that there is a transmission. So with coherent transmission T, it goes through, and with or it goes to the, which is square root of 1 minus eta, it goes to the environmental mode. So this means that a creation operator, a dagger, goes into square root of a dagger and square root of 1 minus, so square root of eta a dagger, sorry, and square root of 1 minus eta a dagger environment, okay? So if you would have a, and with this calculation, we can then do it for any D-mode system if we do it for one mode. If you have a particle number n, like a pure state like this, then this is described, of course, as this operator acting on the vacuum. Sorry, I forgot the vacuum here. And this operator goes now to the nth power of that operator with the, then there is this divisor acting on the vacuum of the chip and of the environment. And what happens if you expand this? I'm just expanding it. It's just the algebra here, and you get this here. What you get here is actually what is the probability, or well, the amplitude that you make k photons and n minus k in the environment, and the absolute value square of this is actually the probability of this. And just this simple model is basically enough. Of course, for each mode, you have to have a different eta to actually pretty well describe these lossy boson sampling and Gaussian boson sampling experiments. And this we will do in the hands-on session. Right, and actually, I'm done with the theory part. So what should we do? Should we start with the hands-on session? Maybe we can start with the exercise number, like pip install, I guess that would be a good part, right?
So thank you for joining the hands-on session. In this hands-on session, what we will do is that we will solve certain problems which are included in this lecture note, at the end of the lecture note of chapter 1, which are these 6 exercises. So for these 6 exercises, we will have 60 minutes, so 10 minutes for each exercise each. The first one is pretty simple, install Picasso. So we will do this together. Oh, that version doesn't exist with, in Picasso, but anyway, we should just do a pip install Picasso. I don't know. Let me close these environments. I will create a new environment. Let me call it Picasso graph or something like this. Oh yeah, I have to make this directory. And I just create a file, right? So let me just open an editor, and I will create a new environment for myself. Or just install Picasso here. Zoom. Okay. You can see it, right? Okay. So you can install Picasso via pip. And yes, and if we open a Python terminal, then we can see that if the pip and the Python uses the same, or the pip uses the same Python, then you can import Picasso. And it is imported now. It takes a bit of time because of the compilation. At first. Shouldn't take this much time though. Has anyone been successful? Or is it just mine? Okay, it has been successful. So the next import is faster now. So the first import is always slower because there needs to be some compilation done. Okay. So we are successful in this. And the next task is to, yeah, so we opened the Python terminal and we imported it. And using Picasso, the next exercise says that we should prepare a Fock state, which Zoltán already told about what a Fock state is, using the sampling simulator. I will explain what the sampling simulator is in a moment. And we should use, after this, a particle number measurement or photon detection to simulate photon detection and obtain samples from it. Okay, so let's do this. I will call this. I will create a new file. I will open my editor. Anyone can open. Yeah.
May I have a question?
Yes, sure.
It installed version 6.1. Is okay?
It's okay. Yeah. I had so this is a typo there. It should be 6.1. I will correct it in the next version of the lecture notes. Yeah, sure.
Right.
I just thought that I will publish a 6.2 when I started to write the lecture notes, but I didn't in the end. So yeah. Okay. So 6.1 is fine. Actually, 5 is also fine. So yeah. Anyway, so I will create a new file and let's call it um, because I think we will use the same file. So anyway, let's call it this. And as you have already seen, we should import Picasso. But what I generally do is to use this abbreviation for Picasso, PQ, because it will be much easier for us later. Okay, and the task is to prepare a Fock state using the sampling simulator. And of course, you can look at the documentation. I didn't mention is that there is a documentation on in redox with Picasso, and you can already see a simple code example of Picasso, and it tells you how to define a program. So let's copy this. So the pattern is the following: with program, with pq.program as program. This will create a program instance. In this program instance essentially contains the list of instructions in Picasso. And what we do first is to write down this queue. In this queue, this is just like a syntactic sugar. In this queue, you get to specify the modes on which you want to apply your instruction. By the way, tell me if I should slow down or if there is any question. If not, then I will continue. So I wrote down this pq.q and I will write pq.vacuum. And this means, as the docstring also explains, that it prepares the system in the vacuum state, which has been introduced by Zoltán already, right? We didn't execute anything yet. We are just writing the program or like the list of instructions. And okay, so before I specify anything, let me just quickly try to execute it. But in order to execute it, we need to instantiate a simulator instance. So what we should do, this is like the example. This is for the Gaussian simulator. This is the one which we will use the most. But because we are not we don't know Gaussian states yet, we will use the sampling simulator, which is for simulating boson sampling. So we will do sampling simulator. And we should specify the number of modes. Let it be 2. So we use the convention that the D is the number of modes, right? Okay. And this is like a very basic simulator. And with the simulator, we can call execute. And to the execute, we can specify a program, basically. And it will give back a result. This is like the basic structure of a Picasso program. right? And now we can execute it. Let's try executing it. And what I usually do is that I usually execute it on a terminal, and I write -e because it will drop me into a Python terminal. This is like quite convenient now. And what was the name? First exercise. No such instruction implemented for this. What did I do wrong? There is no vacuum here. Sorry. We should have done. We shouldn't have done vacuum. We should have done the state vector, by the way. So we should have done specifying. Sorry. Yeah, the Fock state 1, 1, right? So in the sampling simulator, the vacuum doesn't make any sense, which is, yeah, because you cannot do boson sampling on a vacuum, so, or it doesn't make any sense, so it doesn't support it. So, so state vector, we can specify in state vector the occupation numbers, and the occupation numbers can be given as a tuple. So it's a tuple of 1, 1. That would mean this state 1, 1. Okay, I just left it in a comment. And yes, I wanted to do it like this. Yes, and it will drop me in a Python terminal. Okay, and we have a result. The result, there is samples attribute, but there are no samples here because we didn't perform any measurement, and there is a state attribute. Okay, and what can we say about the state attribute? We can, for example, check out the we can also check out the simulators, what kind of simulators we have, and we can also click on boson sampling simulator, what it does, but we can also check out the boson sampling state in Picasso, and it will tell us all the relevant methods that we might want to use. So for example, very simple example, we want to use this get particle detection probability. It will return the particle number detection probability specified in the argument. So that is the occupation number. So let me write the state here. So state, I will copy it into the file as well. But we have now a sampling state, and in this sampling state we can write get particle number, particle detection probability. And we can also specify the occupation number, and the occupation number should be, for example, 1, 1. And this is, as we expected, this is 1. And if we check out others, for example, 2, 0, this is 0. So we have done it well, right? I will copy this into the what did I want to copy? This one. Just to have it here. I didn't copy it well. Okay. Yeah. So this concludes the first exercise. So if we execute this, then it will print out the probability. Anyway. So this was easy. I promise that the next ones will be a bit harder. Did you follow? Is anyone lost? Is it understandable? Should I speed up? Okay, so let's proceed. Apply a beam splitter. So if we proceed to the next exercise, it says that we should apply a 50-50 beam splitter on the prepared state. from the previous exercise, so on the Fock state 1, 1, and apply photon detection. And it also says that we should estimate the probability of the output patterns, which we might do or might not do. We will see. So here, what we should do is that it said that we should apply a beam splitter. So I'm applying a beam splitter. And if I leave the parameters as it is, it doesn't change. It will be a 50-50 beam splitter. But you could just write 50-50 also. That also works. It doesn't really matter. Anyway, yes? Yes.
Sorry, so a question, because right now I understand that I can still use the pq.q in the beam splitter instruction, because the only two modes that are there are the modes that I instantiated the state of.
Yes, but in practice you should. I mean,
I understand. It's okay. I'm just making sure.
Yes, yeah. We don't throw an error if I mean the empty unfolds to 0, 1. Basically, you should think about it. That's it. Yes. Yes, and how you specify a detection. You also do this, and you do a particle number measurement, and that's it. So that inputs in your measurement or in your setup photon detector on all modes, right? Technically, you can do it in like some modes, but we don't do it now. And I will delete this. Sorry, and I will put it into comment. Now we can execute it. So to get the probability, you don't need the particle number measurement. The particle number measurement, what essentially it gives back to you are samples. So it won't give you probabilities, it will give you samples. As many samples as you specify. So, okay. Let's execute it. And then I will show what happened. So in result, there is a sample. This is 0, 2. Okay. So if you reach for resulted samples, it will be a list of tuples, and the tuples will contain the measured particle numbers. And the measurement results, yes. And this is only one. Instead of executing it many times, we can provide a parameter here in here in execute. We can provide how many times should it execute it, and we can provide, for example, 20. I wrote 20 here, and now I can. Okay, I will come out. I will rerun this. It executes it with 20 shots. Shots meaning the number of samples should be taken. And we see the samples. Do you see it now? I think you see this thing here, which is in a very unfortunate. This is better here. I will also bring you guys up here.
Very nice demonstration of something very interesting.
This is intentional. This is very interesting. So you can see that the probability of detecting 1, 1 is like, it's very low. So it's technically 0. So it's, yeah. And you can also see that the samples are either 2, 0 or 0, 2, basically. This is called the Hongo-Mandel effect. I don't know if you've heard it. Yes.
How is it called?
Hongo-Mandel effect. HOM effect. Yes. So it's very interesting. You can see that Phew. Can I write here? Yes. So what happened here? What we did is that we input 1, 1 here. We applied a beam splitter, which is a 50-50 beam splitter. And we do some measurements. Okay. We do particle number measurements, and whatever comes out is like 2, 0 or 0, 2. This is what we did. And no 1, 1 comes out, which is very, very interesting because we started with that one. Yeah, it's a bit paradoxical, but it's quantum mechanics, so yeah, we should expect this.
Classical thing, if that would be just a 50-50 chance for one to go in the same way or go back, it would be 1 for like 25%, 2, 0, 25%, 0 to a 50%, 1, 1. And now
Yeah. Yeah, it happens because of the interference. Yes. Yeah, so we displayed the Hongo-Mandel effect in Picasso. Great. Did you follow this? I mean, we didn't derive it at this point. We can derive it, or we can show that this is indeed true. What we have seen this.
I have a question which is completely like silly and technical,
Okay.
but I see that the results I obtain are not zeros and ones or twos and zeros, but NP int of 64.
Yeah.
What's going on? I mean, you have just tuples, and I have tuples of boxed basically numbers.
It's typical. They're packing this.
So that is
this type annotation.
You don't have to care about that. So it might be because you use it uses some different version of number or something like that, and it might return with.
Okay.
But this is a 0 or 2, but it is like a NumPy type of 0.
Yeah, I know. I mean, I know what it means.
The same.
Okay, I installed with JAX. That might be. Install Picasso with JAX.
Ah, yes. That should, I mean, we don't use JAX here, so it shouldn't really change the packages around. It could happen that you have a different OS and like different, I don't know, versions of, I don't know, number is compatible with that, and maybe that version of number does this.
Okay.
But it's functionally the same.
Yeah, I understand. Yeah, but just...
It's so nice, right?
Yeah, it's not so nice.
Sorry about this. What should I do?
I can unbox them, of course.
No, I mean, if you want to use it, then you can use it. I mean, it's the same object,
Yeah,
almost. So, but yeah, it doesn't look nice on the screen. Yes,
Yeah.
I agree.
Yeah, that was my problem.
The reason I don't know this is a problem because in my computer it isn't a problem. So for me it works. Yes. Okay. Yes. Okay. So I think we should proceed now. Or I mean, is there any more questions? No question. Then proceed. Okay. Next exercise. Derive the probabilities of detecting the outcomes 2, 0, 1, 1, 0, 2. Verify that this corresponds to the probabilities acquired by Picasso simulations. Very good exercise. Okay. Let's do this. How should I do this? There are multiple ways of doing this. One is that we can use the formula for the permanent, which Zoltán has already shown, or we can derive it from first principles also. So we can derive it using the ladder operators. I think I will go with the second one because I mean, depends on the time. How much time do we have? Don't worry. Okay, I won't worry about time. Okay, let's do this. How does this work? If I do this, can I grab it? That's great. Okay. So I think this was the number for it. Okay, let's try doing this. We know that the initial state is something like 1, 1. But Zoltán has already mentioned it, that we can write it as A dagger 1, A dagger 2, applied to the vacuum. Here, okay, so we can write the vacuum as this, but what we generally do is that we write it just like this. Doesn't matter. I mean, vacuum is vacuum. So we don't write 2 zeros here because yeah, in at multiple modes. So if we have multiple modes, then it will be tiresome to do this. Okay, and what we do is to apply an interferometer to it. How do we do that? How can I grab this? Okay, so apply interferometer. So this is like the first step. The second step is this. Is that we apply this interferometer. But this interferometer, let me write it with a hat here, just to say that this is an operator. Okay. And this can be written as U A1 dagger A2 dagger 0, 0. Okay. Is this clear at this point? This U, I didn't really specify it here yet. It is in the formula. You can find it in the lecture notes for this beam splitter. But you can also find the relations on how it transforms the creation and annihilation operators. I believe, yes, you can find it also here. But this is the formula, which you can see. And in our case, you can say that, of course, this is labeled by modes, and this is also parameters. But in our case, what we can write is that this u is something like e to the power of and pi over 4, and this is, I think, a0 a dagger, not 0, sorry. Start labeling from 1. Plus. I think it is a plus. And is there an I here? I think. Right? Is this the formula? Did I copy it correctly? No, there is a minus, of course. So all the phi's are zeros, and there is a minus. Yeah, sorry. Always mess this up. Yes, like this. Okay, so this is the formula. And we can say, I mean, it might have also been said, or it is obvious from this, that if you expand this exponential, and if you apply this to the 0, 0 state, then the higher order terms in the expansion will just map this vacuum state to 0, right? So we can say, should I derive it, or is it clear that I just want to say that U0 is just 0? This has already been mentioned by Zoltán. So if it is clear, then we can say that, so continuing this, I will write an asterisk here, we can say that we can insert the identity several times. So we can insert an identity here. I will insert an identity here and insert an identity here. And we use the fact that the identity is nothing else but u hat dagger u because of unitarity.
Can I have a fundamental question?
Fundamental, okay.
Yeah, in the sense that A1, A2, dagger, whatever, they are Hermitian. So we have e to the power of
They are not Hermitian. Or what do you mean Hermitian? Which is what is
They are not Hermitian, the AI, A2, no?
No.
Okay, so this is the question was about I missing there.
Yes.
So there is something like different from like typical quantum gates and quantum Hamiltonians.
No. So it is not. Yeah. So the dagger operation maps the creation operator into an annihilation operator, right? So what we have. Uh, can I switch color somehow, or I don't know. I will write a little cloud here just to make ourselves remember that AI dagger is AI dagger. So the dagger is there for a reason, because it is indeed the adjoint in the. Sorry? Yes.
Yeah, but that was not about I index, but I as imaginary, and that's the reason why it's fundamental. Because I mean, naively, I would expect to have I here, and you know what you're doing, and I'm lost.
Okay. Let me show that this is indeed unitary. So I mean, what you usually write is that u is equal to e to the I h hat or something like this. And you can say that h hat, I mean, you have this condition that h hat dagger is h hat. That's how it becomes unitary. But you can equivalently say that you can write it as e to the some operator a, and we can say that a dagger must be minus itself. It's skew Hermitian. Okay, and we can show. I mean, I don't know if it's good now because of this I coming up here. So if you conjugate the I, then that will bring a minus sign here. Here, I didn't put the I here because this operator in the exponential is already or skew Hermitian. Therefore, it is unitary.
Okay, that it makes clear.
Okay. So it is clear now. The skew this is skew Hermitian. So skew Hermitian, or maybe they say anti-Hermitian. Both, I think. Okay, but this is okay, right? So let me put this away. Can I? Oof. Oh, I left the hats there. I mean, I just want some space here. Okay. Yes. So what we did is that we now that it is clear, we inserted the identities here, and we can expand the identities as u dagger u hat, and we have u dagger u hat here, and we have also an A2, and we also inserted one here. I will delete this cloud here. Sorry, this cloud ends here. Okay, So we have inserted, just to remember, these are identities. And yeah, I don't write out the heads on the creation and annihilation operators now. I forget it, sorry. But I think it is clear now because we don't denote anything else with A. Okay, but we can also say that this is the vacuum state because the interferometers leave the vacuum invariant. The interferometers don't create particles. Or you can also derive it from the formula for this unitary here. So what we have is U A1 dagger, U dagger, U A2 dagger. This is also a dagger, U dagger. Apply to 0. Okay, this is great. Because now what we did is that we translated the evolution of a quantum state into the evolution of not observables but operators, evolution of the ladder operators, the creation operator specifically, right? Is this clear now? What we have done here? Great. Tell me if you have any question. So yes. Oh, I think I will delete this. I think I will. Poof. Can I delete this? I don't know how. I cannot delete this one. This is very slow. No. Okay. Yes. Yes. Oh, sorry. I just. Okay. This is good. And so what we do is to, I mean, we didn't exactly derive this formula. We will derive it in the next lesson, I think. But we have this formula here, which basically means that the annihilation operators are, and the annihilation operators transform into annihilation operators, and the creation operators transform into creation operators. And we can read off how the creation operators transform under this transformation, right? So what is apparent that this will become up to some signs. This is something like A1 dagger plus A2 dagger square root of 2. And this is, because it's, yes, this is, sorry? Yes, it's a 50-50 beam splitter. So that's why we can use it. So sorry, so the T and the R is also real, but 1 over square root as well. Right? So here, so maybe let's try to do it like this, that the J is the first mode and the K is the second mode. Then what will happen is that it is so this is a minus here. So whatever it's just a reflection of the measurement or the setup. So we can choose whichever, right? And we have this here. This is great. This is also a dagger. And we can expand this, or we can multiply this together. Uh, yes. And we will have, of course, if we write it out, this is A1 dagger squared over 2 minus A2 dagger squared over 2. I will put this in parentheses to make it more clear, right? We did this plus there should be, I mean, plus. Yes, let's do the plus. This meets, or like this meets with this, so we will have A1 dagger, A2 dagger over 2 minus this meets with this, because everything commutes. So the we use here that the creation operators commute, and this is 0, right? Yes, and if we continue, or if we push this further, then what we will have is that, of course, I left the vacuum here, and the thing is that, so we can use A1 squared over 2, 0, and A2 dagger squared over 2 apply to 0. Okay, so this is like a superposition of these two states, right? So now it is immediately clear that the 1, 1 won't appear, because what we have is that this A1 squared, so let me just derive it in detail. So A1, A1, 0 is, we know of course that this is 1, this is A1, 1, but from the, and of course I missed the daggers here, but we know from the relation which can be found in the lecture notes, regarding the where is it, the creation operators. Here is it. So if we use this one, a dagger n is equal to the square root of n plus 1, and the state n plus 1, right? We use it here. Then we will get square root of 2, 2, right? So we can write this, I will put this in parentheses, we can write this as, so square root of 2, but this will be divided by 2, 1 over square root of 2. There will be a 2, 0 plus a 0, 2. If I do it for the other mode as well. And this is the end. Yeah, minus. Sure. It doesn't matter in yes, but there should be. It's important that we keep it. Yes, sure. Thank you. Any questions? Was it clear? Should I speed up? Should I be slower? Okay. Okay. Now we can explain the measurement results. In the measurement results, of course, the minus one won't make a difference, or the minus sign here before this 0, 2. Okay. Okay. Now let's go back to the exercises. Phew. Yes. Okay, so we have 2 exercises left, and we have how much time do we have? 25 minutes. Okay. But we started at 45. Then we don't have okay, anyway. Okay. So we have to consider this state. Oh, I need to charge my laptop. Just one moment. So we need to consider this state 4. So we are on single modes now, and this and we have this state 4, and we want to apply photon loss to it. And the question is, what is the probability of detecting 2 photons in a subsequent photon detection? That's the question. Is it possible that no photons remain? And now I will go to this section here, and we will see what the loss does. I mean, of course, we have the formulas here, so we can immediately answer the questions, right? So here, if we see this formula, if we would start with a 4, right? So n equals to 4, then we would end up with, maybe I can copy this formula. I will grab it. Yes. Copy. And I will write 1.7.5, I think. And I will put it here. Okay. And we say that, okay, we have n equals to 4, and eta is 1/2, right? And the question is, what is the coefficient of k equal to 2? This is like pretty easy. It's a substitution. So what we do here is that I mean, we should just read off the coefficient. The coefficient is like square root of 4/2, which is something, and this is like the 1 over square root of 2 to the power of 2, and this is also, yeah, this is also 1 over square root of 2 to the power of 2. So the coefficient is this one. So this means that this is square root of what is so it is this is, I think, 4, something like this. Anyway, this is this value, but the point is that this is just an amplitude. We need to take the square of this. So the probability that we will detect this the k equal 2, so we will only have k equal to particles remaining, is the coefficient squared, basically. So this is something like this. We can just write like this, and this is it okay? Pretty straightforward calculation. Okay. And now we have the last exercise. Yeah, we can model this setup in Picasso using an environmental mode and the beam splitter. Verify that the state vector corresponds to the expected state vector using Picasso. Okay, so what we can do now is that we can reuse the same program, basically. Instead of the previous state vector, we should use a 4, 0, right? And we should decipher what the beam splitter angle should be. So I will create this new one here. We know that this eta, from this discussion in the lecture notes, that this eta should be, or the square root of eta should be the cosine of that angle. So the square root of eta should be the cosine of some angle. But if the eta is 0.5, 0.5, then this should be 1 over square root of 2, right? So what should be the angle? So the angle should be pi over 3. Am I right? I think I'm right. 4 pi over 4. Yeah, sure. Okay. Whew. So this should be pi over 4. Yeah, okay, yeah, this is logical. Because then this is like a same beam splitter, same 50-50 beam splitter that we used. Maybe I should have input another number. And what we want is that we don't want to measure the particle numbers now because we are not doing any particle number detections, but we want to figure out what is the probability of detecting what 2, right? Because that will correspond to two particle which remain in the system. So the first mode is like the our original mode, and the second mode is the environmental mode. And the 2 corresponds to two particle remaining in our current mode, and two particle going to the environmental mode. And we want to calculate this probability, and this probability is this one, and this corresponds, right? So Picasso works. And
I don't get one thing.
okay.
Why? I mean, can you show me the code once again? Because
Sorry.
why do you apply beam splitter on the both of modes?
Yeah, so the setup, okay, how we model losses. Maybe I should have included a picture. Let me include a picture
Yeah.
now, because that will make things apparent. So what we do is that we have this 4 here, and somehow due to, I don't know, absorption or whatnot, we will have photon losses. And we want to model these photon losses. In order to model these, so we don't want to model absorption or any of these actual physical processes. What we want to do is to put it into a beam splitter, for example, with some angle theta. This angle theta is parameterizing the amount of loss which this Fock state will suffer. And with this beam splitter, we couple it to a vacuum. It's not necessary to be a vacuum. It could be any state. It can also be a thermal state if you want to be realistic. But it's a vacuum now. Okay, and this is what we do, and we can, I don't know. So this is like in the note I wrote env here just to denote that this is like an environmental mode or ancilla mode. We don't really care about this. And we ask the probability here, probability of detecting 2 here. Of course, if the beam splitter is like, I don't know if the parameter is like 0 or something, then it does nothing, right? So it will be like it is the case when there is no loss, right? Okay. Any question? Is this clear now? How?
Yeah. What was my problem is that I assumed that beam splitter acts only on one Q mode for some reason.
No, it cannot act on one Q mode. It can only act on two Q modes. That's how it is defined. And we make it. So I mean, we only have one mode, so that's the trick. But we add another.
Yeah,
so
the typical trick with environment tracing out the environment.
yeah,
but
yeah.
Okay.
Yeah, of course. Yeah. So of course, if we would trace out the environment, then we would have a mixed state of corresponding to the different probabilities or the different possibilities of detecting 0, 1, 2, etc. And of course, we know that it could also happen that in the end we won't detect any photon, so we will lose every photon. So yes, I mean that was like a question in the exercise. I'm saying it because of this. Okay, so I think that I mean, if there is no more question, we went through all the exercises basically. I believe so. And we still have we can still have a coffee break until the next part, which is about Gaussian states. Is it okay if we have just a 15-minute coffee break? Okay. Then thank you so much.
Yeah, so we'll continue at 2 p.m. Right?
Yeah. Okay. Okay, you can see my screen, right? Okay. So, unlike Zoltan, I don't have uh, presentation prepared, but I will not slides. Yes, exactly. So so I don't have slides, but everything is written down in the lecture notes, which are in the Indico. This is updated. I will update this like every before each chapter. Basically, I will update it. So tomorrow morning there will also be an update because I didn't finish that yet. Anyway, today we will work with Gaussian states. So, it's chapter 2, Gaussian states. Why are we interested in Gaussian states? We're interested in Gaussian states because experimentally they are basically more feasible than single photon states or Fock states. It is very difficult to experimentally produce those states, but Gaussian states are pretty natural in quantum optics, and we will see why. Um, so these Gaussian states have many interesting properties, as we will see, and these are very tractable by using their first and second moments. We will also see this, but first we want to discuss some elementary photonic quantum states. So elementary photonic. Yes. Okay. So I will define these states. The first one is that we already have seen by Zoltán is the vacuum state. Just for completeness, I will write it down. It is defined by the fact that all the annihilation operators map it to 0 for all I modes. This is the thing. This is the first or the most basic state that we will work with. This thing, this vacuum state, is Gaussian, as we will see in the next, maybe after the break, basically. The following, or the next one, is the squeeze state. Why is this state squeezed? we will see tomorrow why we call it squeeze, but the thing is that in the phase space picture, it is squeezed along one direction. From the definition, it is not at all clear, but we will see if we learn some quantum optics. Okay. So the squeeze state is defined as the squeezing gate applied to a vacuum state, and Z could be any complex number here. So yes, and the next one is coherent state. The coherent state is defined as this, as d alpha 0. And alpha can also be any complex number. And it is confusing because we also put cat in the squeeze state, or like a symbol inside the cat in the squeeze state, and a symbol also for the coherent state. But the convention is that if we put a Latin character inside a cat, then it is a squeeze state. If we put a Greek character or a Greek letter, then it is a coherent state. Okay, this is like the common convention. Okay, these all three are Gaussian states. We will show this later as well. And okay, so these are all pure states, but states are not necessarily um, pure, so they can be mixed. And the common mixed state is the thermal state, which I define like this. I make these definitions at first, or like the first thing in this talk, because I will refer to them and I don't want to introduce them in the middle of a discussion. So a single mode thermal state has this form. So it is something like this. So I give it as like with its coefficients or amplitudes, like coefficients, yes, like this. This is also in power. Yes. This is a thermal state. And there is this parameter n bar here. N bar is just the average number of photons in this state, right? Is this clear so far? Question?
Wait, is it like cyclical definition? You are defining a row with n and n with row?
No, no. I mean, it's not a definition. N is a free. It's a free parameter.
Mm-hmm.
Free parameter. But incidentally, the average number of photons is exactly this parameter. So if you calculate this could also be an exercise, is to determine that this is indeed the average number of photons in this thermal state. So
okay, thanks.
Yes. Questions? Okay. So I mean, you can look at it as, so these coefficients are, this is like a probability distribution, and the how should I put it? The expectation value of the probability distribution is the average number of photons. So yes. Okay. So after this, I will still not tell you what Gaussian states are, but I will talk about the characterization of linear gates via the symplectic group. Okay. So first I will define what is the symplectic group, and then I will show how it comes up in linear optics. So linear gates. symplectic group. Okay, so the fact that it is a group is useful, but it is not important. So it's not important to know what is a group. So it's yeah, but symplectic. What does symplectic mean? Symplectic is like I think it is a Greek word for complex. It used to be called complex group, but then there were also other things which are called complex groups, so they renamed it to symplectic. It has to do something with the complex number or complex structure. I will define it now. Let me open a new page. Yes. So the symplectic group is defined as the following set of matrices is all the 2D by 2D matrices which fulfill the following relation. Oh my God. I will have to charge my laptop. Okay. Okay, so what is J here? So J is nothing else but this matrix. This is, in general, it could be any non-singular skew-symmetric matrix, but it is chosen as, or we will choose it as this matrix. Here there are zeros. Okay. That is like the set of symplectic matrices or the symplectic group. Okay. And we will show that this will describe linear optical gates with quadratic Hamiltonians. So linear gates or Gaussian gates, as somebody might call it. Okay. So we will use another form of this, which is like this complexified version of this. You remember the transformation matrix for the between the ladder operators and the quadrature operators. You remember that there was this formula. So psi is like the vector of creation, annihilation, and creation operators. And this one is like the vector of quadrature operators, right? And P1, PD. So in the chi, these operators are self-adjoint, but in psi, these are not self-adjoint. These are the creation and annihilation operators. And sometimes it is easier to work with creation annihilation operators. Sometimes it is easier to work with the quadrature operators. And in quantum optics, we tend to switch between them many times, which is quite tiresome. I agree. So that's why if we want to work in the ladder operator basis, as we will see, or the creation annihilation operator basis, we can transform this symplectic group into a complex form, and we can say that this is this set where we do this transformation, basis transformation of these symplectic matrices, where we remember now that the relation is that as far as I remember, that it is psi equals to W chi, right? should be like this. So this is like the transformation rule, and we can switch between the two bases. Bases meaning ladder operators or quadrature operators. Okay. So anyway, I will show that the transformations exactly which will preserve the canonical commutational relations, which Zoltán has already talked about, are exactly these symplectic transformations. Okay, so I mean, I will not show this because it is a lot of time, but I will show it as a I mean, I will state it as a proposition. It is proposition 1, stating that if we have like a transformation on the ladder operator, so for example, transform it by some S matrix, we don't know in advance what this matrix is, and we transform the operators, or like the vector of creation annihilation operators. Let me put an underline here, just to denote that these are vectors, or like at least vectors of operators. But let's say that we have this transformation. So when S is like a 2D by 2D matrix. Then we can say, so for example, we can write this W as some kind of transformed creation annihilation operators. So it could be B1, etc. And these are operators as well. BD, B1 dagger, etc. BD dagger. And we show, or we say, or we want to enforce the canonical commutational relations. So when we say that this BI, BJ dagger admit this relation, and also they must admit, or they must commute like ladder creation operators with creation operators and annihilation operators with annihilation operators. So we can say BI, BJ should be 0. Sorry? Yeah, the identity, yes, it's missing there. So yes, so when this is true, then it must be that S must be an element of this complex version of the symplectic group, basically. Sorry, this is D. Yes, here it is D. Okay, because we are in D mode.
Sorry, so complex version, you mean a complex representation of this symplectic group, just representation of the group?
Yes, this one.
Mhm.
So I meant this one. So we transformed the symplectic group. I mean, originally the symplectic group of, how do I? Sorry. So originally the symplectic group is defined like this, right? And this J basically encapsulates the canonical commutational relations between the quadrature operators. And we could have started from that one. But it is more convenient to start with a group, or start with something which encapsulates the canonical commutational relations between the annihilation and creation operators. And basically the relation is modified as follows. So I didn't write it down, but the symplectic groups or symplectic matrices in this complex form admit a very similar relation. It admits this kind of relation that S, K, S dagger should be K, where K is a matrix like this: identity and minus identity. We could have also started from this definition, but there will be some theorems which will have a statement about the symplectic group and not this complex version or complex form of the symplectic group. So there will be matrix decompositions which will be more convenient in this symplectic group basis, or like this original rail basis. Yes. Yeah, sure.
Yes, so can you, did you now motivate what these symplectic matrices describe?
Not yet. I mean, I will tell what these.
Okay, so
I mean, I already mentioned that these will describe the linear optical gates, or these will characterize linear optical gates.
meaning that they will be like somehow coefficients of,
Yeah.
yes, coefficients of when you apply a linear optical gate on some operator.
Yeah, actually, we have seen these. So if we look at the lecture notes, or Zoltan's presentation, but it's almost the same. If we look at these matrices, for example, for the what I'm showing you here is like the matrix which describes how the ladder operators transform. This matrix here, this is like a symplectic matrix. But more generally, for the beam splitter, this is also a symplectic matrix. In these different bases, because we are describing it with ladder operators. For the squeezing as well, you have this formula, but for the squeezing, because it is squeezing, so it squeezes along one quadrature. So for example, the position quadrature, it is very handy to have it in this quadrature basis, and it is diagonal in this basis. And we will use this. So that's why quantum optics people switch between these two bases all of the time. Right? Okay, so we have written down here, but down here these relations for specific gates, but we didn't prove it that it is indeed the case, and we don't know if we have like a generic linear optical unitary, right? How does it decompose into more elementary gates? So that is like a question, and the statement is that with squeezings, beam splitters, and phase shifters and displacements, you can write down any linear optical transformation. Okay, so that is what we want to show, and that will lead us to like the like from Gaussian states, how to actually implement Gaussian states or all the possible Gaussian states on a photonic quantum computer. That will give us a circuit, and that will be good for us if we want to do Gaussian boson sampling. Is there a question? Did I answer your question? Okay. Okay, but I didn't say anything yet. So I only said here at this point that the symplectic group somehow preserves the canonical commutation relations. This is very interesting, and but I didn't. Isn't immediately clear that the ladder operators, or how should I put it, that the linear gates can be described by these. So let's do this. So proposition 2. It's not necessary to put it in a proposition, but I just like to organize it this way. So consider a linear optical gate described by this unitary operator where H has the form this. and these are vectors. And I will explain what I mean by this brev here, or I don't know how you pronounce it. Breve, this accent. This is like a Slavic accent. This denotes, for me, or in my convention, this thing here. So like you put or you concatenate together the vector and its conjugate. I will use this because it's like it appears everywhere in quantum optics, and this is like a common convention. And this psi here is like our usual psi containing the operators, the ladder operators, right? So this Hamiltonian here, if we want to write it down, then this could be written as equivalently um, it could be written as something like alpha I AI plus Hermitian conjugate. So what is the difference? Or there is a difference? I didn't know. Oh my God. Okay. Sorry. Then it's okay. Then I will switch it to Czech accents like, immediately after I go. Okay. Okay. So the thing is that here, so if we do this, and if we want to calculate the evolution of the ladder operators, how do I go down? So the statement is this: if we calculate this one here, by which I mean that I go through all the elements, so I understand it element-wise, this conjugation or this application of U dagger U from the left and right, that it goes element-wise. So it applies to the A1, it is applied to the A2, etc. It is a vector. Yes. 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 So by this, I mean this. So it's like it's a shorthand notation, but it's, you know, it is what it is. So what I'm saying is that this is nothing else than this thing here. This is like your handy J, which is I'm writing it down. This is this matrix. And an identity operator, because it must be an operator. Okay.
No, okay. I mean,
okay, not okay.
It's not straightforward to say.
To follow. Okay. So I is the imaginary unit. J is like is a matrix. It's a 2D by 2D. And this is also a complex vector of length 2D. This is equal to, and this is equal to, like, this is equal to something like alpha vector and alpha vector conjugate, something. This is also vector. So I tend to skip the underlines, but this is also a vector.
Okay, so why there is identity? Why do you multiply everything by identity?
So by identity, I mean, okay, so this will be a vector. So all of this will be of some vector, right? And this has elements. So this will be some vector uh, 1. So I can collect it in a vector, right? So if I use this notation, is this okay? So I can expand it in a vector, and to each vector element, I put an identity. So I put the identity in the vector.
Okay, so this notation is not clear.
This is like a...
You have to leave this multiplication. In Julia, for example, I mean, we use this dot to show that you map basically you apply a function on every element of a vector or a list. So it requires additional notation because it's really unclear here.
Yeah, so I agree that it is like it's very difficult to come up with like good notation. This is also this breve is not always used. They use some kind of other Greek letter or something like that. I don't know. So how do you say that? How should we?
Maybe a dot at the bottom for multiplication, because then
Dot at the bottom. So like this?
yeah, no, not here, but lower in the between alpha and 1 at the line. Yeah.
Oh, this is very
Yeah, but that's
science.
Yeah, that is a very computer science, but
Okay.
at least there is, some indication that it's unusual.
Yeah, yeah, I agree. But okay, physicists tend to use it without any problem. I mean, yeah, it's unclear in many contexts. Yeah, so it's
Yeah, but physicists use it, but I'm not a physicist, and I try to understand what's going on. And decoding HC, for example, took me a couple of years without guidance. Once I got it, it was clear. But
yeah.
it is very dense notation is a barrier to entry.
Yes.
Okay, at the end of the day, it is complicated, but actually manageable. I mean, this is a set of operation that you can, mostly linear operation, that you can understand. Basically, addition and multiplication. There's no much there, but the language is complicated, and the fact that the objects are not well defined. I mean, there's no definition of what are the actual objects. You have to define what belongs to what, because otherwise, I mean, this is shorthand notation that you have to understand it already to understand it, basically, to be able to read it.
Yeah. So yeah, there are many shorthand notations here. So I'm sorry about this.
It's not your fault. It is physicists' fault, for many years already.
It is how it is written usually. But of course you can think that okay, so you apply this u dagger u to this xi, and xi is like a vector of operators of length 2D. So you cannot apply the unitary to the vector itself. So there must be something else.
But it is not written. It is not written there,
But it is not written.
Yeah, it has to be clear.
Yeah.
Excuse me, where are operators on the right-hand side?
Because, okay, so in the right-hand side, it is like a vector of operators. Again, because you started from a vector of operators, and on the right-hand side, as in the left-hand side, there should be a vector of operators, but each operator in this vector is an identity multiplied by this thing here. Also, there should be an I, but yes. This is just the statement. We can also derive it. So it's like maybe it is easier if we derive it. I don't know if we have time for this. Probably we don't.
So maybe I lost it a little bit. So which unitary are you applying now?
The unitary, which has this linear Hamiltonian, like not linear optical. Truly linear.
Truly linear, yes, yes,
Truly
yes.
linear.
But so in each of the components you have an identity, but you also should have a linear combination of A's, right?
No. No, so the thing is that the A's will oh yeah.
Yes. Okay.
Yeah, sure. So xi plus this. There's a typo in the and it only makes sense this way. So this is a statement that the yes.
Okay, now it makes sense.
Yes, yes. So you have all the creation and annihilation plus identities. With
Yes.
some sort.
Yeah, sorry about this. Yes. I don't know what happened with the yeah. Anyway, so this is one statement. So that means that the ladder operators will transform by shifting, or will transform by shifting. Or what I wanted to say is that if you have like this linear Hamiltonian, then the linear Hamiltonian will not rotate the ladder operators, but it will shift them. So it is like an affine transformation. Okay. So the statement is, or the general statement is that the linear Hamiltonians will describe linear transformations of ladder operators, and the quadratic Hamiltonians will describe like rotations of the like with matrix multiplication, rotation of the ladder operators. This is like the next proposition. So in the proposition 3. So the proposition 3 is like very similar, so that if you have like similar unitary, but H looks like psi dagger H psi, and this should be understood as Ij goes from 1 to 2D, Hij psi, and this is vectors. Now and then these are the vector elements. This. So this is like a matrix vector product, or like a inner product basically. So this is like this is why it's quadratic. It will be quadratic in the ladder operators, quadratic Hamiltonian. And if we do this, similarly as before, the ladder operators, or the vector of the ladder operators, will transform as something like this. And this is an S. And S is, I mean, I will tell a few things about this S. The first thing is that this S is is coming from this complex version of the symplectic group in. It's in here. And we also know the form of this. So we can also calculate this. So, sorry, I use a different notation here. We can also calculate this, and to calculate this, we just need to exponentiate this one here. And just to remind you, K is this matrix. And H is defined in this quadratic form of ladder operators. Okay, so H is from here, and this is the definition. Okay, so the statement, or like the main statement, I will put it in a box, is this. This is like the most important thing for our case. And this also should be understood on the level of like psi is a vector of length 2D of operators basically, and S is, it doesn't do this element-wise matrix multiplication because it doesn't make sense. S is like a finite matrix. It transforms the vector of ladder operators, right? So just to make it clear, or is it clear? Maybe I should ask this question. So
Never clear here.
It's never clear.
Okay, but so basically we are creating linear combinations of the ladder operators. And okay, and those operations are restricted to the symplectic group. I mean, the combinations are restricted to symplectic group in order to, I don't know, preserve some physical properties, which I'm not aware now of. In this language, it makes very clear because we have very nice understanding of, I mean, this is like very nice representation of.
Yes, it is nice representation. We have to get acquainted with this, or we have to get used to this because so now it is a bit difficult to understand, but we will understand everything much better if we understand this, how this symplectic group is connected to the linear optical transformations, and how, or like the linear optical quantum gates will transform the ladder operators, because many things, as we have seen already in the hands-on session, that, for example, the evolution of any state by a passive operation can be written as the evolution of ladder operators. So if we can characterize the evolution of ladder operators, which is basically this equation, then we can write many things down, or we can calculate many things. And this is like the key to like Gaussian states. And also yeah, Gaussian boson sampling. Okay, I won't prove this now because it is a bit involved, but I have written down in the lecture notes. And maybe if you read them, maybe it will become a bit more clear. So the derivation is not difficult at all. So we are using like the same knowledge which we have been talking about. Hey.
So can I just add something? Like,
Yes.
Zoli wrote it down very nicely in the text, but what Piotr pointed out that could be also done. So if you have a unitary which is such that if you take U dagger and ladder operator and U, and then it's a linear combination of, again, ladder operators, okay, then of course it turns out that if you would take this transformed ladder operator and another ladder operator, then the commutation relations has to be the same because of unitarity, and that it's an identity there. And on its own, it already gives you actually a condition on these coefficients, how they are linearly. Actually, that condition is exactly the symplectic condition. And what Zoli says additionally, that actually those Hamiltonians even generate all of them.
Yeah. Yeah, so the first one is that if it preserves the canonical commutation relations, or it preserves the, like, yeah, then it must be symplectic, and also the quadratic or like linear optical Hamiltonians, or like the quadratic, so the purely quadratic, which is from proposition 3, the purely quadratics will give you all the symplectic ones. So that's why it is nice. Question?
I have question. I have question to the notes. In the notes you have at the end of the proof, 230, you have gamma comma SC.
230. Equation 230.
Yeah, equation 230. It's like notation. The question is about notation because once again,
No,
I'm lost.
This is like, okay, so I didn't mention this, but in the lecture notes I defined this affine symplectic group because you see that there is like a linear term in the Hamiltonian and there is a quadratic term in the Hamiltonian, and the quadratic is like the symplectic matrix and the linear term is like this gamma vector which you can see here. And this affine symplectic group is like the symplectic group plus R to the 2D. So, and there is like a multiplication defined over this group. And this is like the action of the group on the vector of ladder operators. So that's how it is defined. So and the parenthesis and the comma is there because it is like a direct product. So an element of a direct product. From definition, what definition? From definition 2.2.2, basically. So if it is not clear, if it is not entirely clear now, I don't think it's that much of a problem. We will see some exercises and we will try to calculate some of these relations. Okay. And now I will talk about Gaussian states. Or I mean, I have 10 minutes, right? Or how much time do I have? What is like the does any organizer know the okay. So the definition of a Gaussian state is quite, I mean, it's a bit involved, but also not that involved. So it also uses linear optical Hamiltonians. So like a definition. For the definition, what we will need? Linear optical Hamiltonian. Which we will denote by H. And so we remember that this linear optical Hamiltonian is of the form of like if we want to put it in the short notation, this plus alpha, there is this breve, and psi. Okay, so this is like a very generic one. The condition is that H must be positive definite. And there is a very good reason why this should be positive definite. So if it would not be positive definite, it would be, yeah, it would not even define a state, I think. So, or it would be ill-defined. So that only works that if H is positive definite. Also, we can, yeah. So this is good. And states of the form, let me write it like this, just very informally. Is the set of all density operators, or like the density operator of Gaussian states, is this set. So we divide by its trace. So this is like the exponential of minus beta. Minus beta. Beta is usually something called the inverse temperature, but it is like a parameter which is non-negative. No, it's positive. It must be positive. Sure. And so I will write it down that beta is positive and H is S here. Okay. So this is like the, I mean here that these are the density matrices. So this is as usual. So for a physicist, I think physicists usually see these ones. For example, in statistical physics, you can immediately see that this is normalized, and you can also, I mean, it's not immediate, but you can also show that this is mixed in general. But if you take if you take the beta going to infinity limit, you will get pure Gaussian states.
So in order to make it more clear, those are mixed and pure states defined on Fock basis for a single mode. And of course, I mean, Fock basis, like in case of mixed, it's operators of a Fock basis.
Well, I didn't choose a basis here, but yes. I mean,
but that's basically, I mean, those are the being we are working with. I mean, because when you don't, okay, so sometimes it is difficult to understand when there is no like domain or of these objects. That's the question.
okay. So yeah, so in order to make it a bit more mathematically, so we should have introduced like the Fock space rigorously a bit more, and also yeah. So I should mention that. Okay, so this is like a bounded operator on this bosonic Fock space, which we have already talked about informally. So, and I mean, yeah, and also self-adjoint. So because it's a density operator, but you can also see that it's self-adjoint because the H hat is also self-adjoint. So, and also the trace of it is, so it's a trace class because the trace of it is one. So yes, question?
From a physicist. Well, in simple statistical physics, we have this beta is usually inversely proportional to temperature. So when you write beta goes to infinity, you say temperature goes to 0.
Yes.
Great, superconducting qubits go this way. But in photonics, we want to do ambient temperature machines. So, but still is bosons. So I guess he would keep the Gaussian state quite pure, no? Or what do you expect?
So what is the question exactly? So temperature, or what is the effect of temperature?
What is the problem of not having pure Gaussian states?
So the problem, what do you mean problem? So like you want to prepare something, right? And generally you want to prepare like pure states. So for example, in the GBS setup, you want to prepare a pure state because the adjacency matrix of your graph will be like it only makes sense that way if you have like a pure state.
It doesn't have to be
in this
Gaussian, though.
application.
Mhm.
Sorry?
It's just it doesn't have to be Gaussian in another mindset, let's say, like with another kind of machine, right? It's architecture dependent, or you want to keep a Gaussian state in any architecture? I don't think so.
So you're saying that Gaussian state is architecture dependent, or that's what you're asking?
For me, a Gaussian state is a mathematical tool. It's not a physical object. So
Yes.
But what do you mean by that? It's in some sense it's a physical object because these are the ones that we can create these in.
So like in practice we realize it with, I mean
it's just that I don't call millikelvins something easy. And we speak about photonic quantum computing here means higher temperature should not be a problem. And it's just beta going to infinity is triggering me. Okay, we can.
Yes. That's partially true, but this is not the way you do it really. So what you do is that you sort of do a squeezing on the vacuum. So you have, I mean, the vacuum state you can get different ways. You don't have to put like very low temperature. In fact, for photonics, you don't have to have that low temperature than for superconducting qubits and so on.
Because yeah, you have few photons, so you can change this. Okay. All right.
Yeah.
Also, it doesn't necessarily have to do with the actual temperature in the interferometer, I believe. So, I mean, it's some parameter here, so it's not necessarily that you have a Gaussian state, and this is like the temperature of the
Yeah, of course, temperature is just one subset of that.
Yeah, of course, it has to do something with that, but
yeah. Thank you.
Okay. Okay. So let's go through an example here because it is or how much time do we have? What did I promise? Okay. It's almost up. Should we? Okay. Who wants to have a coffee break? Oh. Okay. Okay. So vacuum state. It's Gaussian. Okay, so I want to show this just as an example, just to, I don't know, just to really understand the definition of a Gaussian state. So let's take H equal to this A dagger A, which is like the number operator. And this in the Fock space. So we are in single mode, so we don't have so we are not in the multiple mode setup. We have only a single mode. We don't have any labels here. And we can write this number operator as this. This is logical because applied to a Fock state, it will return the number of particles in that particular state. So it should be this form. Is it clear? So if A dagger A is applied to N, then it should return N, right? And we know this. And if you do it with this one, with this object, that also does the same. Okay. So n goes from 0 to n, n, apply to, let's say that it is m here. Okay, just a slight modification. I apply to m here. But this is delta of nm. This is like the Kronecker delta. So this sum is n equal to 0 to infinity n delta nm, and understand it well. So it collapses to m, right? So this is just a side calculation here. So we can write it like this, right? And it is diagonal. So that's why we are doing this. And also, so we can write that if we exponentiate this, so if we exponentiate this e to the beta h, which is our number operator, then it will become this one here. Right? Right. Okay. Because it's a diagonal operator and we can do it without question. So do the exponentiation on the coefficients, and we can also show that this one, which is essentially the sum of the coefficients. It will be a geometric sum. It will be something like this, right? So this is the normalization. So what we can say is that the rho, or like the state or density, the density matrix, sorry for doing this. The density matrix, depending on the inverse temperature, is something like, we have this formula. Sorry. Is this okay? So this is like in the this trace is in the denominator, so it will come in the denominator, right? And this is it. And the thing is that okay, so this is definitely a Gaussian state. This is actually the thermal state, or a thermal state. So if we compare it with the definition of the thermal state, it is a thermal state. This is just a remark. With this parameter. You remember the thermal state, which I introduced earlier, right? And this is the parameter of this thermal state. This is actually the average number of photons, right? And now, if we take, so I'm saying that just think about it. Yeah, it could be because so if beta goes to infinity, yeah, there should be a minus sign. I think there should be a minus sign. So here. Yeah. No, because if we go with beta to infinity, then no, it should be a positive, I think. It should be a positive. Don't fool me, Tomek. No, okay. So the reason I'm saying is that if we take, let's see if it works. So it will decide it. If we take beta going to infinity, this should be the vacuum, right? If beta goes to infinity, then this thing goes to 1 minus infinity. This will go to 0. Maybe there is a plus sign here. Let's do it like this. Right. Maybe there is a typo in the yeah, but yeah, this makes sense that it should be like this. So if we take beta to infinity, then we can see that this is like indeed the vacuum state, right? Is this clear? Because if you take beta to infinity here, then this will go to 0, this term will go to 0, and this term, if beta is yeah, this, yeah, so yeah, except the n equals 0, yes. So this is indeed the vacuum state, and this is pure, as I have advertised it. Yes. Okay. So we can have coffee break now. So I mean, I think this is prime time for a coffee break. This was the definition of Gaussian states. But this is, I mean, is there any question first before I go on? Did any question come up in the break or something?
Okay, so what is the motivation of calling the states the Gaussian states? Because until now there is no Gaussian here.
Very good question. Very good question. Okay, this is Gaussian because the Wigner function of the state will be a Gaussian function. That's the answer. We will need to get to the Wigner function at some point, which will be tomorrow. So at this point, there is no Gaussianity apparent whatsoever, right?
Okay. Obviously, I don't know what's the Wigner function apart of hearing it many times.
Okay.
But yeah, that's a good answer.
Yeah, you will know it tomorrow. Although there will be indications here because we will define something called the covariance matrix here. And this covariance matrix will exactly be the covariance matrix of the Gaussian distribution, which is a Gaussian distribution, which is the Wigner function. So, so in general, photonic states can have Wigner functions which are not Gaussian. It can also go to negative and whatnot. Also, Fock states are not Gaussian, so they have like very wobbly Wigner functions. We will talk about these, but this is where it comes from. Okay. Yes. Okay, we have defined Gaussian states. We also discussed why is it Gaussian, and we want to write something about time evolution of Gaussian states, which will be useful later. So I write it down now. It's this thing that if you want to time evolve a Gaussian state, so if you want to write something u rho u dagger, then it will become something like, so if we expand the definition, we can write it like this. This is one step. I could include the UU dagger inside the trace on the both on the left and the right hand side because it's an insertion of the identity and using the cyclicity of the trace, which is also true in this setup. And we can also write it further like this. The trace is the same. So what I did, so the conjugation by this U dagger or this U can be, I mean, you can move it up into the exponent basically. So what you observe, okay, observe. What can you observe here? So if U H hat U dagger is still quadratic, that implies that U rho U dagger is also Gaussian. Nice.
By quadratic, you mean not affine?
Sorry?
Oh, wait, by quadratic?
Oh, by linear optical. Sorry. I meant linear optical. Yes. Sorry. So not necessarily quadratic, but it can also contain linear terms. Sure. And okay, you can ask, but Zoltán, the Hamiltonian matrix, you said that the Hamiltonian matrix has to be positive definite. But the thing is that if we So that also needs to be preserved. But the thing is that if you apply, I mean that is a clue that you should apply linear optical quantum gates, and these linear optical quantum gates will preserve the second order of this Hamiltonian. So it will still be second order, because we remember that so if we conjugate a creation or an annihilation operator, then it will still be like a creation or like linear combination of uh, crea- uh, creation and annihilation operator, but not powers. So it will not become like a polynomial of like these ladder operators, right? So what all I want to say is that uh, so for example, let's take h equal to like this quadratic, right? Aij, psi I, psi j. And if you do like this linear or this time evolution, then of course ij is going from 1 to 2D. Then we will see that this is the same sum. Right? And you will have u psi j, u dagger. And I inserted an identity here.
Okay, but wait. Now it is your lifted operation, as far as I understand, because xi is the vector of operators, isn't it?
Yes.
So this is this lifted, what I call with this dot at the bottom operation, isn't it?
I think so. If that what you mean, that the conjugation by this unitary.
No, what I mean is that xi is not a matrix.
Ci is an operator. Psi vector or xi.
Okay, this I. Yeah, okay, this is I operator. Yeah, okay, yeah. Sorry. Yeah, that's the point. Yes, of course.
Yes.
So it's a okay xi operator.
Yes, exactly. And you know that this thing, I will switch color. That this thing is something like sum of s I j psi j. And j is going from 1 to 2D. Okay. So this is like a linear combination of the ladder operators. And this is also like a this is also a linear combination of ladder operators, right? So this is also the same quantity. It should be from K. Also, I should use like a different index here. So let me fix this. So just to make it consistent, this should be an L or something. So L goes from 1 to 2D, S, J, L, C, L, right? And we can write it further. So if we go further, we can see so that this is like a sum over ij. Everything goes from 1 to 2D. This could be rewritten to something like LKL, going from 1 to 2D, SHS, dagger. How does dagger come into play? Yeah, the dagger comes into play here because, sorry, I missed that. It should be a dagger here. Yeah, because in the definition, if we see in the definition, there was a dagger here in the left-hand side. That is like the convention, and here is also a dagger here. So that is also like a there is also like a conjugation here, right? Okay. Question?
Yeah, I mean, we had some discussion, and because I don't understand the
Okay.
Psi K, Psi K and L, they are ladder operators, and the question was my question was, what is the algebraic structure of the ladder operators? Because if you just work, for example, typically with Hermitian, you cannot multiply to Hermitian to be Hermitian. But in case of ladder operators, is it closed under multiplication? That it's not obvious for me.
So like if you close or if you multiply two ladder operators together, okay. So the thing is that this is something called, how should I put it? So you should consider the ladder operators as like elements of a polynomial ring, basically, but you factor out by the canonical commutational relations, basically. That's the algebra here. So it's like an associative algebra formed by these ladder operators with these relations. And if you multiply a ladder operator with itself, or like you take some power of it, then that is that. So you cannot. There is no. It doesn't happen that. So if that's the question, it doesn't happen that a dagger square is something a dagger or something. There is nothing like this. Okay. So the canonical commutational relations are all the relations, nothing else. Is this okay?
Yeah, in a way. I mean, probably it's hidden in your response that. So, but my question is whether Psi K times Psi L makes sense in the this multiplication of these operators, whether it is like still something. I mean, of course it is because you're doing that, but how it is that it is, how it happens, what is the mathematical foundation for that it makes sense in this in this language.
Well, it's composition of operators, right? So for example, you can say that okay, mm, I don't know, differential operator is like an operator. It acts on functions and it produces another function. Not necessarily L2, but anyway, so it produces something. It is the same with these operators. So you can think of these as like I don't know, like differential operators. And if you apply twice, then that's that. So that's how you do it. So actually, so this comes from this um, description of the wave function of the harmonic oscillators, where you have like this multiplication operator that is called x, and this differential operator times minus I that is called p, and the ladder operators are linear combinations of those. We have seen that we have seen these relations, how to define the creation and annihilation operators, and there is no problem by defining that. Okay, you differentiate twice in this variable, or you multiply twice with this symbol x, like variable also. Okay. Um, of course, so it's like, are these bounded operators? Not necessarily. Why? There can be things that go wrong here, uh, but we can still talk about them. Just we have to be careful. Okay. Question? No question. Okay. So that means, okay, we have seen that this Hamiltonian is transformed by this symplectic matrix, right? So we have seen earlier that the evolution of the ladder operators can be characterized by these symplectic matrices S. So I will denote symplectic matrices by S. And you can, so it amounts to a conjugation of the Hamiltonian. Is this okay? And that means that the Hamiltonian will stay positive definite. So it's important that you will still get a Gaussian state. It's not that important. So okay. Okay. So but you can see now that this is very powerful because you can also do it backwards, right? So if you have a Hamiltonian, then can you decompose it into like somehow into this form? Uh, can you decompose arbitrary Hamiltonians such that H is some kind of S the S dagger, right? And S symplectic and the D is somehow diagonal. Why do we want to do this? We want to do this because we want to decompose it into like multiple independent harmonic, or I won't say harmonic oscillators, but multiple independent Gaussian states mixed up with some kind of transformation, which will be an interferometer, as we will later see. Right? Is this clear what I'm trying to do? So I'm thinking backwards. So if you apply a quadratic or sorry, a linear optical Hamiltonian, that will induce a symplectic transformation in the Hamiltonian, in the parent Hamiltonian of the Gaussian state. And the question is, can we do it backwards? So if we decompose this Hamiltonian, then if we are thinking backwards, then this symplectic matrix will amount to a linear optical gate, basically. And that's the main idea here. And that's why.
And you can simulate then one type of Hamiltonians using these devices, these Gaussian boson interferometers.
Sorry?
So is it like motivation? I'm guessing that your motivation is that if you have Hamiltonian that you would like to study, whatever it is,
Yes.
once you find this decomposition of, let's say, in practice, approximate decomposition, whatever you do,
Yes.
then you can basically use this Gaussian bosonic quantum computer to study this Hamiltonian.
Yes, yes. So given any Hamiltonian, whichever Hamiltonian, I will provide you a way to like I will give you a circuit basically, right? And it will be a simple circuit, but just we have to go through with this and because immediately, so if you look at the Hamiltonian, it is immediately not clear how to implement it in a quantum computer, and it is indeed a bit difficult, a bit more involved, and that's why we are yeah we are here. Okay, so now maybe I start a new page. Now I want to talk about the normal mode decomposition. This is exactly what I was saying. That there is this, I will call it a proposition. It is the fourth proposition. It is, yes, it is the normal mode decomposition. That if we have like H positive definite uh, like yeah Hamiltonian matrix which is appearing in the quadratic Hamiltonians or linear optical Hamiltonians, then um, then we can decompose it as H is S d S dagger, right? And yes, so S is symplectic. And you can also understand it in the ladder operator basis, and you can also understand it in the quadrature basis. But so in the but the point is that there is a difference between the diagonal. So D is diagonal, and thing is that if in the quadrature basis, which we didn't work with, it is truly diagonal. It is something like diag of nu, and this is also another overloading, or like it's a very weird notation. It is, yeah, you might not like it. This is like the act of putting these vectors into the diagonal, basically. So it's like nu1, nu-d, nu1, nu-d.
Yeah, but that's pretty standard in the sense that
Okay.
that's, in MATLAB you have this kind of operation. Okay, you would have to collect them, but like join them, but together, but doesn't matter.
Okay. And nu are coming from, so these are the eigenvalues. Doesn't matter. Some numbers. Doesn't matter. I mean, you can calculate it. I mean, you can imagine that there is like some kind of decomposition. You can call a function in Python or MATLAB or something like this, and does this decomposition, right? Okay. And
Excuse me, what do you mean by quadrature basis here?
quadrature basis is the basis of
EP.
yeah, the X and P.
Ah.
Okay. And yeah, and if you want to do it in the ladder operator basis, then you will transform this diagonal accordingly. So, but it looks nicer if we do it in this quadrature basis, right? So the thing is that that equivalently. So if you have this Hamiltonian, you can write it either in this basis with the psi, and you can write it equivalently with chi, which is this chi transpose, because dagger doesn't make any sense here, and I would say xp here, or maybe I could write quadrature, but xp is like more telling, right? You can also write it like this, and you can say indeed that if you decompose it, so you can say that okay, it is some kind of S D S transpose now, because it is everything is real here. Now you can write it as, or maybe it is more convenient to put the transpose here. Like you can choose it where to put it, because yeah. So the transpose of a symplectic matrix is still symplectic. You can write it as S psi transpose, and you understand it on the level of vectors, so like on the level of vectors of operators, right? Because S is like, again, it is like a 2D by 2D matrix, and here you write D like this, right? And you can also, I don't know, give a name to these transformed operators, right? But you can write it definitely that if you do this operation, like, yeah, argue with the following, that okay, you can find some transformation like u psi u dagger psi u, which gives this, right? Then we can write it as u dagger how should I write this? Okay, and this is like the diagonalized Hamiltonian. Is this clear? Maybe you have question. And if you so if you want to write this down, so this is a very simple form. So I'm finishing up by writing it down in this very simple form. The Hamiltonian will look like something like this. So it will be a sum of independent Hamiltonians, basically. These are like single mode Hamiltonians. Okay, so why did I do this? Here it became apparent that if you apply a symplectic apply a linear optical transformation, it becomes a symplectic transformation in the level of the Hamiltonian, or in the level of the Hamiltonian of the Gaussian state. And with this symplectic transformation, you can transform this Gaussian state into like multiple single mode Gaussian states, right?
So you can start with single mode Gaussian states and then mix them up and to obtain something interesting.
And you can obtain everything, basically. Every Gaussian state. That is the idea. Okay. And now, okay, so you can say that we need to obtain all the symplectic transformations. I mean, how do you decompose or obtain all the linear optical gates, right? How do you decompose the linear optical gates? So now we know that the decomposition of Gaussian state is like, I don't know, we reduced it to the decomposition of any linear optical gate. Okay. I don't know how much time we have. We might have zero time, basically. We should end at 5 p.m. The covariance matrix and the okay. So the covariance, yeah, we calculate covariance matrices. But the okay, so let's keep the decomposition of the symplectic, yeah, of the linear gates, because it might be too much. Maybe we can delay it until tomorrow, but it is written down. It is called the Bloch-Messier decomposition. Okay, and now, so just to finish it quickly. We are interested in the statistical moments of Gaussian states. In fact, we are so interested that Gaussian states can also be defined by these statistical moments. the first and second statistical moments entirely characterize the Gaussian states. We can also define Gaussian states like this. And this is defined, or the first statistical moment is defined as trace of rho. Let me write it like this in the complex basis, because we will use it more often. This is like the first statistical moment, and this is like a vector, and these are the, so by I denote the elements. So mu c is like a vector of length 2D, and sigma ij is this thing, which is fairly complicated, or looks fairly complicated, but is well motivated. Yes, I do a dagger here. There is an identity operator here. And here, by this notation, by these braces, I mean the anti-commutator. Okay. And okay, you can say it fine. No, I didn't want to do this. So this is called this one is called the covariance matrix. And this is called the mean vector. And you can define analogous quantities in the quadrature basis or quadrature operator basis as well. And for example, we can say this might be a useful example, that the vacuum state is very simple in that sense, that the mean vector of it is like 0, 0, and the covariance matrix of it is just like an identity, a 2x2 identity. Okay, so it is very simple. And why is it interesting for us? Or it is also interesting for us because we can easily derive transformation rules for these vectors, for this covariance matrix, for example. So the transformation rules are, as I said, the linear optical gates will transform Gaussian states into Gaussian states, and they admit, or they have something called a symplectic matrix, which characterize the time evolution of the ladder operators. And incidentally, these first and second moments are written in terms of the ladder operators. So if we evolve the state rho, this can be moved to the evolution of the first and second moments. And hence, we can write the evolution as with symplectic matrices as follows. So if we have some kind of transformation U dagger psi U transforming like this, transforming the ladder operators like this, then this vector, this first moment vector, will be transformed as this. Opa. Very simple. And the covariance matrix will transform like this. No, I won't. Yeah. Is this clear? So. Do you have any questions? Because this is like the last thing I wanted to.
Okay, that's I have a crazy question. When you have Gaussian states, we can imagine that you could have like higher order states in the sense that they could be skewed somehow, or you could use higher moments basically, or non-zero higher moments.
Yes.
And does it happen? Is it like something physical, or is just a stupid question? Oh. Yeah, I mean higher order states. It's like you could, I mean, do this reasoning for higher orders too, as I understand, and it might be useful.
So for example, you can say that you define that you define the statistical moments up to third order, and until after that, you I don't know somehow infer from that, or what do you mean?
Yeah, for example, I mean, you can have like classically you can have distributions that are that have moments up to, let's say, third or fourth order that are non-zero, and then you have just zero moments.
Exactly. What?
You cannot have that. Actually, that's the funny thing with this distribution. So at the second you can cut off, but the third you cannot.
You mean
there will be then a small fourth cumulant, fifth cumulant, and so on.
But for optical distributions or any
distribution? No. I'm talking about classical probability distribution.
Classical? Okay.
Even for classical distributions, it's not clear. If you prescribe the moment, will it give like a probability?
Yes, and the zeros can only appear if you prescribe it up to 2 and then zeros. Otherwise, like infinitely zeros cannot appear.
Okay.
Also, you cannot. I mean, if you talk quantumly in this quantum optics sense, you cannot have like any distribution because of Heisenberg uncertainty principle. So you cannot have like a Kronecker delta or like a dot or something like that. So it has to have some kind of width, on some direction. We didn't talk about Wigner functions yet, but this is the case that it cannot be anything. So there are also constraints on that. It's called the Robertson-Schrödinger uncertainty relation. Fun fact. So yes, this is all I wanted to say. I didn't have time to decompose the linear optical gates, but we can talk about it later. But for the exercises, it's not necessarily needed, and it's something that is written down also in the literature. So.
Can I point one more thing here? That this transformation, this is true for, of course, for statistical moments of any states, not only Gaussian. For Gaussian,
yes,
what happens is that actually these moments already define everything.
Yeah, by linear optical gates, yes.
Yeah, by linear optical gates for any state this would hold.
Yes. No, because you don't use the Gaussianity when you derive this. So you only use how the ladder operators are transformed under linear optical gates. Okay, so if there is no more question, then we can go to the exercises, if that is good for you. Because we don't have much time, let's go to those. So I think what I will do is that I will copy, like in a very ugly manner, copy the exercises. Yes, like this, so that I don't have to switch that often. Oh my God. Okay. Okay. So, exercises. The first one is It's not like connected to this Gaussian formalism, but it is still a very useful exercise. Calculate the probability of detecting zero photons in a coherent state. We know what a coherent state is. And we want to calculate what is the probability that if we measure particle numbers in this coherent state, what is the like probability of detecting zero photons, right? And there is a hint that we should use this formula, which I will underline here. This is not clear why it is true now at this point. You have to use something called the Baker-Campbell-Hausdorff formula. But yeah, I didn't want to talk about it at this point. Okay, so let's derive this. Is there any question regarding the exercise? Zoltán?
So you will also use this and calculate with Picasso the same thing.
Yeah, we will also calculate with Picasso.
Maybe let's do that first, no?
Let's do that first. Okay, let's do that first. Okay. Okay, then let's do that first. Let's make another editor. Let's open another. Sorry. Second exercise. Okay. So what we can do, or what Zoltán said, is that we have to calculate the overlap of, or like the particle number detection probability in a coherent state. How do we prepare a coherent state? You see my screen, right? I have to import Picasso. And to prepare a coherent state, you're right. Yes. So you have to prepare it in a vacuum. So we start from a vacuum state, and then we apply displacement with, let's say that, okay, so alpha is r times e to the I phi, but we use this convention. Let it be 0.1. R is 0.1, right? This is the magnitude of alpha, basically. And what we want to do, okay, so if we would execute it like this, then we would get a displaced state, and we could look at its state vector basically. Simulator is something called the Gaussian simulator, and we want to use one modes. So we have one photonic modes, and we can just execute this program, right? And we will get a result, but we can immediately get the state of this. So state equals, because the result contains the state and the samples, we want to have the state. And let's say, okay, I think I can execute this. So this is the program, and I will execute it interactively. Yes. Yeah. This is not a PDB. Okay. So we will have this state object here, and in the state object, okay, we can check out the documentation of Picasso. What is like the documentation? So you can find it online, the documentation. In the documentation, you can see that what kinds of methods and attributes does it have. And for example, it has, what should we use here? We can calculate its density matrix, basically, which would give it. Or Yeah, let's do that. So it calculates the density matrix. It is fairly long because, yeah, it's not really trivial, and it would have been easier to do it in the Fock state. Yes, and in the density matrix, you see that this is like the value, or you take the diagonal, and the diagonal will contain the particle number detection probabilities, as for any density matrix. Also, I should point out that this is like a matrix, but in practice, it should be an operator. But we cannot do it for infinite dimensions. The Fock space is an infinite dimensional Hilbert space. We cannot do it. We cut it off somewhere, and Picasso cuts it up here. Okay, so we calculate this density matrix, and we calculate this 0, 0 element, right? And it is this. And now we want to compare it. So it has like a very high probability of detecting it at 0. So it's not a very big displacement, right? And we want to calculate it analytically as well. So let's do that. Let's go back to this XOR now. And let's verify that this is indeed that quantity. So we can write immediately that 0 alpha is something like 0, a displacement operator, a displacement gate, and 0. Okay. And now what we want to calculate is that, okay, how the displacement is applied to the vacuum. And in order to do that, we use this hint here, which I underlined with red here. We can say that this is nothing else than, let me check it again. Yes. E alpha A dagger, E this one, and there is like a phase factor coming in, which will be important. Um, yes. Yes, like this. I hope this is true. Okay. And now, I fear that the minus sign is missing, but let's see. Now we can calculate this one. This is nothing else than alpha bar A dagger A, right? But we know that A dagger A is minus identity because of the canonical commutation relations, right? And also, yes, that we know. And this is good at this point. So we can write that this is nothing else than, because it's an identity, it doesn't do anything. It's just a constant factor in front of this expectation value. This is minus alpha squared over 2. And we have this expression remaining here, e to the alpha I dagger and e to the alpha A, right? This is good. But we notice that, okay, that e to the alpha bar A 0 is nothing else. If we expand it as follows, it is nothing else than alpha to the power of n, A to the power of n, divided by n factorial, and goes from 0 to infinity, applied to 0. But we know that but we know that if we apply an annihilation operator to the uh, vacuum, then we will get 0. So it is just 0. And we notice cat 0, cat 0. Because for n equals 0, then you will get like a 0th power of the annihilation operator, and it is identity. Okay. And this is basically the same, but it's adjoint, right? Of this one. So this is still 0 as well. So we get, if I write it further, e to the this one. Because this inner product or this product here is 1. So this is like the formula, right? And we had in the code alpha equal to 0.1, right? So we can write it should be 0.1 squared divided by 2 and e to the minus. So we should verify this. So I will import an numpy because for exponentiation I need this. This is installed with Picasso, so you don't need to install numpy by yourself. You can check that this is indeed 0.1 squared divided by 2. Yes. One thing that I didn't mention. That's why I shouldn't have tried this. The thing is that if you use Picasso, there is an automatic scaling. If you will look at the instructions, if you look at displacement, then you will see that because so it has a certain dimension, which is h bar. So the specified displacement is automatically scaled by this quantity. So it is automatically scaled by 2. So in order to rescale it, we have to divide it by 2. Sorry about this. So h bar is like something that is appearing between the conversion of quadrature operators and ladder operators. And that's why it is in there, because in order to make the relations for transforming the quadrature operators meaningful, we have to scale it by this square root of 2 times h bar. So this is like a nuance thing which we have to do here. So we have to divide it by 2 because in Picasso, so let me specify it. So let h bar equal to 1 for simplicity, and in config we can specify h bar equal to h bar, and here we can just divide by the square root of that. This made things a bit more difficult, but yes, I think that is fine. Yes, and now we will have the good or the a good result. Yes. Sorry about this. Yeah, code. Yes. Yeah, so yeah, this is like a nuance thing. So yeah, it's like you only have to care about this when so you have a specific displacements and you have to have it exactly this, and but of course you can turn the h bar to 1.5 and it will disappear, which is okay. Yeah. Was this clear what happened? Is there a question? So just to reiterate, what happened is that the yeah, that we calculated this overlap. This is this formula. Okay, let's continue. Okay. So okay. Now what we do is we do it with the pure Fock simulator, and we prepare like a coherent state using the displacement instruction, and then we calculate its norm and justify why it is not 1. So sorry, just to reiterate what is like the exercise. It says that we should use the pure Fock simulator, prepare coherent states like we had before using the displacement, and then just check the norm of this state, or the state vector, the norm of the state vector, and we should verify that the norm increases by increasing the cutoff, which I didn't talk about yet, but I will. Okay, so how do we do this? We do this by switching to a pure Fock simulator. We can have this displacement, whatever. I mean, it's not necessary for now to have this. We have a state, and let's calculate this state vector. State vector. This is like an attribute of the state, and we can print it out, basically. Or we can just print the state, and maybe it will also print out the state vector. Sorry. Let us run it. Okay. So the thing is that if we run it and we print out the state, then the state will. So this is like the occupation number representation of it, or the Fock basis representation. In the first term, you have the coefficient, and the second one is the occupation number. That it. Yes, sure. So the H bar is not important here. Because it simulates pure Fock states, so that we don't track the density matrix, we only track the state vector. It's truncated, yes. So that's why it doesn't have the norm 1. I mean, we can also verify this, that if we print out the state dot norm, then it is, maybe it's a norm. No. Sorry? Yes, but you can set it. So you can say that the cutoff is higher, so you can specify it. So if you specify cutoff equal 20, or let's make it 10, just to not to clutter the output, you will have up to 10 Fock basis states, right? So for example, for this case, 10 is a lot, because the last coefficient is very small. And if you print out the norm with state.norm, then it is 1. I mean, almost 1, of course. I mean, but it got better. a bit. But we also see that for this case, for this small displacement, the norm with the default cutoff, which is 4, it is also quite okay. In config, it's yes. Everything you have to so every kind of like variable you have to set it. Yes, because okay, so then increase the displacement. So if you increase the displacement, let me show it to you. So if it's 1.0 or something, and then I set the cutoff to 2, then you can see that it is pretty abysmal. I mean, yeah. It is still most of it, but yes, it's like 90%, 91%. So still lost a lot. But it is what it is. So the problem with this Fock state-based simulation is that you need to cut it off. You don't have infinite memory. You don't have infinite. You cannot represent an infinite dimensional vector in in Picasso or anywhere. But if you use the Gaussian simulator, then I mean, if you are constrained to Gaussian states, so if you don't want to work with anything else other than Gaussian states, then you can store the first and second moments, and you will have exact time evolution there, which is great. And that's what we will do in the following. I mean, for the next exercise, we will use Gaussian simulator. Is there any question to this? Did you follow? Okay, then let's go with the next exercise. For this, we have to calculate, which is good. Okay, so what do we know? What is the exercise? The exercise is we have to calculate the average number of particles in a coherent state. Okay, we don't know the coherent state, or we don't know how to represent the coherent state in the Fock basis. We didn't talk about it, and we can talk about it later, but it's not important. But we know how the number operator evolves with the displacement gate, right? That's what we want to calculate. So this is like a prime example of why representing the quantum state as moments useful. Okay, so let's do this. So exercise 2.7.3 or something like this. So we want to calculate the average value of the number operator of the displaced or coherent state, which is defined as this one. The alpha dagger and the alpha 0. Okay, this is good. So what is the usual trick which we use? We can write this as a dagger A, right? What trick should we use here? Who knows? Yes. You should always do that. So if you don't know what to do, insert an identity. Or yeah. It's the rule of thumb. And if you see two summations, then exchange it. But yeah. So what we do is that we have this one evolved, and we have the other one evolved. This one we have formulas for. So we have derived. We might not have derived it exactly. We didn't derive it, but we have formulas in the lecture notes. And I will show it to you. It was in the first lecture, basically. Zoltán showed it to us, hopefully. Yes. So what happens with so the annihilation operators are shifted by an alpha, and the creation operators are shifted by alpha bar, alpha conjugate. That's the trick that we have to do. And that's why. So it goes to, or it is equal to a dagger plus alpha bar identity. This is a plus alpha identity, right? So furthermore, we can write that this is, or the evolved number operator is nothing else than a dagger a, if we collect all the terms, plus alpha bar a plus alpha a dagger plus this quantity, this thing here, right? So if we calculate this one, then what it is? Well, what is this? We can write that this is like the a dagger a 0 plus we can write alpha 0 a 0 plus we have alpha 0 a dagger 0 plus alpha star, right? Yes. Okay. So what remains here? This is 0, this is 0, this is 0, and this is 1. So it's alpha squared. And this is consistent with the fact that, so just a quick sanity check, if alpha is 0, then we will still get back 0. And the number of photons, or the average number of photons in the vacuum is 0. So it's logical, right? Okay. Okay. And this, is this okay? Okay. And this can also be done in Picasso. So if we want to simulate this, so let's have a Gaussian simulator, right? And so if we do it with the Gaussian simulator, let's rerun it. Or maybe I could have used the... no. It should be... I mean, it doesn't matter now because we don't calculate the density matrix. It only makes sense if we calculate the density matrix. Of course, from the density matrix, we can also calculate the expect or approximate the expect or the average number of photons, but we can do it directly from the statistical moments because the statistical moments contain it. Okay. Or maybe, yes. We can check it out. If we go into states, we go into Gaussian state, and we can check out what kind of methods we have. There are a bunch of them. There is, for example, this one here, which is like the complex covariance, for example. It is the same Xi what I have talked about here. Okay, so we use the same kind of notation. And also, yeah, maybe one can use this one. So how should we do this? So the thing is that we have to calculate a bit because it also contains the first moment, right? So the displacement is a displaced state is a Gaussian state. We haven't proved this, but we can use this knowledge, and we want to figure out what is contained in the complex basis covariance matrix. So I go back. So we can calculate from Picasso the complex basis covariance matrix, and we can show that. How is this? So the complex basis covariance matrix is something like we have seen that it is the trace of rho. Well, it is defined as this psi I minus this one. Yes, we don't take the adjoint here, but this is equal to the two taking like the coherent state and this anti-commutator here. It is also the same. Right? And we can say that, of course, what are we interested in? So what we want to say is that, for example, so it is a single mode state. So we want to, we are interested in the 1, 1 here. So I is equal to 1 and j is equal to 1, right? So if I substitute everything by 1, then what will I get? That I will get the annihilation operator, so that let me rewrite these. Not two, yes. So it's 1, 1. We need 1 here. But we know that because how we order this psi vector here, it starts with the annihilation operator. So this is basically A1. Or we can write it as A because there is only a single mode, so there is only a single annihilation operator. So I will delete this. So A, right? Is this clear what I'm doing here? So, and now what we can do is that we can expand this and the anti-commutator. So it will be alpha A dagger A alpha plus, so there is this term which anti-commutes with this term, but the anti-commutator of this term, oh sorry. This is still an anti-commutator here. Sorry. Let's write it down like this. It's the identity and A. This is one term, and this is conjugated because of this. Minus there is another one, which is not conjugated. Yes. And also there is like the anti-commutator of the identity by itself. So there is this plus mu1 squared alpha and the anti-commutator of the identity. Is this clear what I'm doing now? Yeah, it's a bit of a long calculation. Yeah, I'm missing the C. Yeah, but this is always C now, so yeah. Yeah, so or maybe it's a tedious calculation and it is too easy, or maybe not that easy. So like it can also be a homework, by the way. So it's like, or no, let's make it. I've seen your impression that we should make it or do this. Okay, I continue. Okay, so what we do? Okay, so we calculate all the anti-commutators like this. So this is A dagger A plus A dagger, right? But we know that if we subtract A dagger A and add A dagger A, this is equal to the commutator of A dagger, which is identity. So this is equal to 2 A dagger A plus an identity, right? For example. And also we can write this immediately that this is 2A. This is 2A dagger, and this is 2 identity. Okay. So that's why sometimes they divide the covariance matrix by 2, because there is a lot of twos appearing because of the anti-commutator. Anyway, so this is nothing else. So if we consider this, we can further write it as the 2 times the number operator, right? And we have this one here from the identity. This is 1. And we have this one here, but this is like the first moment here. So this all of this, I mean, this is like 2 times the first moment of the annihilation operator. So it will be, of course, this multiplied by this one, right? And also it comes out similarly here, that it is 2 times mu1 C conjugated, right? So in total, we will have 4 of these, right? This is like a very, it's a longer calculation than I expected. Sorry about this. It's a bit longer. Yes. Plus we will have one term coming from here, plus 2 times this one, right? So this is nothing else than 2 times this plus plus 1 minus 2 times this one, right? And this was, I emphasize that this was the first, so the one element of the covariance matrix. And this is like the first element of the displacement matrix. And from that, we can deduce so we can rearrange this equation, and we can deduce the the expectation value of the number operator. So in the covariance matrix and in the first or the mean vector, we can or from these we can deduce every first and second statistical moment in whatever basis or whatever form, right? Let's do it with Picasso, but I want to so I wanted to still rearrange this because the thing is that we have this complex covariance here, you know, and that's why it was necessary to rewrite it to this form. So you understand what we are doing? Or there is a method for mean photon number, which we should have used. Yes. Let's try to use this. But anyway, it was a good demonstration, right? So yes. And is it a property or not? No? Okay. And you can also specify modes, but you don't have to. Okay. Okay. And the mean photon. Yeah, okay, I didn't call it. Okay, it's a method. Yes. Yes. And it is a half. Okay, it is 4. What was the R? Sorry. It was 1 divided by yes. Yes. So one is displacement, but there might be an issue with the H bar here. Because so okay, so obviously this is like the square of the 1 over square root of 2. So this will be essentially the square of this, basically, in this way. Yeah, so you can find it. So it's like you can see where it's supported. You can search there is the search bar. For example, it also works for the pure Fock state. Of course, for the pure Fock state, you will not get half less than it because of the cutoff, right? Yeah. So that was that, I think. So in practice, we can do this in the pure Fock simulator. So if we do it with the pure Fock simulator, then okay, so the cutoff is 2. So if we do it like this, then it will be much less. That's the thing. It is also said in the exercise. Where was the exercise? Sorry? Oh, the value of the cutoff was 2.
Yeah, can you go up with the cutoff and show that it goes to 1/2?
I take 20 and it will be approximately. Yeah. Yeah. So that's that. So we have a lot of remaining exercises, but that could be homework. We didn't calculate the covariance matrix of this single mode coherent state or like the squeeze state, which would have been nice. Okay, so the thing is that for calculating the covariance matrix of the coherent state, it is not not bad that we have done this because you have to do very similar calculations like this, right? So, but also you can say that, okay, so roughly what I'm saying, all I'm saying is that if you want to do it quickly, or if you want to do it easily, how you do it is, for example, we have seen that the first moment, for example, if you apply this displacement, or like, let me show it, like, so if you have this, then it will become psi plus some kind of what was it? ij alpha, right? And there was a brev here. Anyway, identity, something like this. So if you calculate the trace of how should I put like the displacement state, right? Or like the displaced state, and you want to calculate the first moment, for example, you can write it as, so I'm not gonna push this to the end because we don't have time, but what you're gonna do is to write it like this, and then you can rewrite it as something like trace 0, 0, right? And this thing here. And here, what you can use is this relation, basically. And this is like the like roughly speaking, this is like the mean vector of this or displacement vector of this Gaussian state. So this is exactly trace of 0, 0 psi plus trace of 0, 0. How is that? ij alpha brev or whatever it is, identity, basically. And here we should understand it like this, that it is this identity is multiplied element-wise in this vector. This is 0, and this is, therefore this is like ij alpha brev. This is the first moment. And the second moment is something similar. End of it. Okay. Finished. It's 5. Okay. Okay. Thank you so much. I hope it was like, yeah. Thank you.
Okay. Okay, so this last statement was the invitation for tomorrow's meeting, and I hope you will enjoy it as well as today. So thanks for coming, and relax and have some rest and take the power for tomorrow meeting. Have a nice day. Bye-bye.